So, hi everyone. Welcome to our ML and or DL deep learning workshop, the second session. So today we will talk about the deep learning part, and I will take the convolutional neural networks, and then Rabiul will talk about the recurrent neural networks later. So the first question is that why deep learning? Why do we use recurrent neural networks or convolutional neural networks? So actually, in the traditional machine learning part, we unlike the image, the computer vision area, the image is originally digital data, so the computers can be very easy to deal with this kind of digital data. But for natural language is like high level human used data. So it is very difficult for computer to understand natural language directly. So we have to use feature engineering to transform the this kind of natural language to digital data, like the vectors, to represent words or sentences. And in last session, we have talked about the TF-IDF feature. So if the question is TF-IDF aware to the word order? And we know that TF-IDF is a word frequency based feature, right? And it's the TF-IDF feature, the TF-IDF vector is used to represent the document or a sentence, a piece of sentence, or multiple sentences. And it is the answer is no, right? And the second question is, can TF-IDF feature capture the contextual information? For example, there are two sentences. The first one is, I will fly a plane someday. And the second one is, the tiny buzzing fly landed on my fresh food while I was eating. So there are in these two sentences, and they have the same word, fly, but the fly in different sentences has different meaning. So we use TF-IDF vector. It's very hard to capture this kind of contextual information. And actually, TF-IDF cannot get the representation of a single word, right? So the question is, what are the good representations of words or sentences? So actually, this is very hard to. This is a very complex definition. So from one aspect, we can say that the words that have close meaning, they will be close to each other in the embedding space. So that's a kind of good representation for words. And so how can we get this? How can we generate, or how can we represent words use this kind of good representation. So today we will talk about how can we better represent words in different sentences and extract the representation of sentences. Use deep learning frameworks like recurrent neural networks and convolutional neural networks. So first, we will talk about the word embedding, word-to-vec, to represent words and in different sentences. And then after that, we will use we will talk about what is convolutional neural network and how to use it to extract the sentence representations. And then I think the third part is the workflow of deep learning project. So I want to summarize the workflow of general deep learning project to give you the sense that when you want to use deep learning to in your project, so which steps you need to take, and what is the construction of this project, and then I will talk about the data flow of the convolutional neural networks. So if you have a very clear picture of the data flow of a model, you will be easier to implement the model by writing code. So the last part, I will show you the code step by step of our convolutional neural network classifier. So the first part is how to represent the word. So actually one of the very naive methods to represent word is the one-hot encoding. So one-hot vector will map the objects or words to fixed length vectors. So for example, if there are 100 words in the vocabulary, the length of the vector will be 100, right? And then so each element in the vector will represent one word. For example, if the first element represent a cat, so the first element will be 1, and the rest of them will be 0. The second is dog, and it will be 1, and the rest will be 0. So the one-hot vector only contains ID, and there is no semantic meaning. And we can see that the inner product of any two of these vectors will be 0. That means there will be no there will be no semantic interaction between any two of these words. But actually, in real world, for example, the man, woman, girl, boy, this kind of word that have semantic, that have close semantic, actually will be close in the embedding space, and their similarity of their representation will be high. Shouldn't be 0. So we can use word-to-vec model to represent the words. So the first model there are two models in word-to-vec. The first one is the skip-gram model. So the skip-gram model assumes that a word can be used to generate the words that surrounded in the text sequence. So for example, for this sentence, the man loves his song. So we can use the we can use central words to predict the context words. And any word in the sentence can be central word. And if we use the window size as 2, so we will use their left 2 and right 2 word. We will use the central word like loves to predict the left 2 words, the man, and the right 2 words, his and song. So if the center word is the, and we will use the center word the to predict the context word in the window size, the man and the loves. So this is actually the concept of the skip graph model is very easy, right? And we will take the step by step to the calculation of the skip graph model. So here we can see that every word in the sentence will have 2 rows. The first row is when the word as central word, and the second row of this word is that context word. So in this model, every word will have 2 kind of representation. So two different representation when they as different role. So here we have 2 representation matrix. First one is here is the central word representation. So the size of this matrix is D and V. So V is the size of the vocabulary, and the D is the size of every word vector. And there are another matrix. This is the context word representation matrix, and the size of this matrix is the same as the central word representation matrix. So first, if we use the one hot representation of the central word, and then we multiply the one hot vector with the central word representation matrix to get the representation of this central word here. This is the first step. And then we can use the representation of the central word multiply with the context word representation matrix to get the result, and the result will be size of V and 1. And then we can use softmax function to softmax function can actually make the can transfer these numbers to probabilities, and the sum of these probabilities will be 1. Here. So here, so we can use these probabilities to predict the context word in these sentences. The last step. So this is the skip graph model, and so in the skip graph model we use the central word to predict the context words in the window size. And there is another word-to-vec model, the continuous back-of-word model. So in the continuous back-of-word model, we use the context words to predict the central word. So this is the difference. This is actually the only difference. So here we use, if the window size, here the window size is 2, and we use the context words, the man, his song, to predict the word loves. So in skip graph model, we use the central words to predict the context word in the window size. And then in the continuous back-of-word model, we use the context words. And how can we get the representation of the context words? We actually average them. We just averaged all the context words in the window size, and the M is the window size. And then we use the representation of the context word to predict the central word. So that's it. Okay, so next part. So do you have any question about the word-to-vec model? So if now we will go straight to the next part, the convolutional neural networks part. And actually, the convolutional neural network is first proposed in computer vision area. And so we will first talk about the two-dimension convolutional neural networks. And then we will talk about how to use convolutional neural networks to in NLP. That's one dimension science. So if we want a computer to recognize the handwritten digital, we will first represent the word 9 with a grid of numbers. So we can use a metric, metric to represent the 9. Actually, the image is a matrix naturally, it's digital data, right? And in the real world, it will be RGB 3 channels of three channels of yeah, and the number will be 0 to 255, right? So, but we just use for simplification, we just use -1 and 1 here. So, but for the computer, if we because this is the handwritten digit, so we can the location of the number will be maybe shifted. And for the computer, the representation of the matrix will change, and it is very hard for the computer to recognize this kind of changes, and it may because this matrix is different, is quite different from this matrix. So it is very hard for the computer to recognize these two metrics as the same thing, the same number 9. But for this kind of variation, the cost is the handwritten digits. So we can use the multi-layer perceptrons to deal with this kind of variation problems. So in the multi-layer perceptrons, we just flatten the matrix to this two-dimension matrix to one-dimension vector. So we just put the numbers one by one. Here, these zeros and 87, 204, 240, 210, and 24. Yep. So this is a 49. The size of this vector is 49. 49 by 1, I think. Yeah. So, and actually, multi-layer perceptron is just the metric multiplication calculation. So, this layer, it will be 49 by 49 matrix. And we just multiply this vector with this matrix, and then we use this matrix to predict, to mapping this the results of this layer to 0 to 9. But for the multi-layer perceptron model, there has some drawbacks. So the first one is the computation complexity. So when the size of the image is very small, so it's not a very big problem. But when the size of the image is very large and it's colorful, that is colorful image, that means there will be 3 channels in the image, red, green, and blue. So the size of the image will be very, very large. And the first layer, the number of the parameters in the first layer will almost to 6 million. And the second layer will be 4 million. So the total number of the parameter in this kind of multi-layer perception model will be 24 million. So this is very large number of parameters, and it will take huge time to calculate the result. And the second drawback is the MLPs will treat the local pixels same as the pixels far apart. And actually, the local actually they are different, right? For example, the pixels close to around the eyes will different from the pixels here in these far apart areas, right? And the MLPs is sensitive to the location of the object, because they just flatten the two-dimensional matrix to one-dimension vector. And if the location of the object changes, and the numbers in the vector will also be changed. So the result may be changed. So let's think about how our humans recognize images, recognize objects in the images. So for human, we will first recognize if this is the coronus eyes, and if this is the coronus nose, and if this is Kronos ears, and if this is Kronos hands and his legs, so and then we will aggregate this kind of features to recognize if this is the koala's head and if this koala's body, and then we will make the decision if this is a koala, right? And the same thing in the the handwritten digit recognition task. So we will first recognize this kind of lines and to the loopy circle pattern. If this is a loopy circle pattern, and if this is a vertical line and diagonal line, and then we will aggregate these features, and then we will make the decision if this is the number 9. So actually in convolutional neural networks, we will do the same thing. So we will make the computer to recognize these tiny features first, and then aggregate them to recognize higher level features, and then higher level features, and then to make the decision if this is this kind of object in these images. So for example, the filter is actually the feature. So for the loopy pattern filter, it will be this 3 by 3 matrix. So and for the vertical line filter, it will be this 3 by 3 matrix. And for the diagonal line filter will be this 3 by 3 matrix. So what is the calculation of the convolutional operation? Actually, we just use the pairwise multiplication calculation. For example, for this filter, we will first use this matrix multiplied with this matrix, but it's not the matrix multiplication. It's the element pairwise. So this -1 multiply 1, and this one, and this one, this one, this one, this -1, this one, and then we will get the sum of this multiplication, and then we average it. So that's the convolution calculation. It's easy, right? And then we will move the filter in this image. So how do we move it? So there is a hyperparameter named stride. So this represents how this area similar to this filter. So we know that we mentioned that this filter is the loopy pattern filter, right? So we will detect in this image if there is a loopy pattern in the image. So when we move the filter in this area, right? This metric is the same as this filter, right? So this summation of the multiplication calculation will be 9, and the average will be 1, right? So it will detect this kind of loopy pattern in this image. So we will move this filter in this image. So how do we move the filter? So there is a hyperparameter named stride. So if the stride is 1, so next time after we calculate this error, next time we will move to this error. We will take 1 step because the stride is 1. If the stride is 2, we will take 2 steps. So 1, 2, and then the next time is this error. We will calculate this error. So if the stride is 1, next time we will calculate this error. And then after we take this, we calculate this error, we will move this way. So next time it will be this error. So in 2-dimension convolutional neural network, the filters will move along to this 2-dimension, these 2 ways, right? And then we can, after we have seen all the errors in the image, we will get this feature map by this kind of calculation. So do you have any questions about this convolutional operation? Yeah, exactly. Yeah, it will detect if there is the loopy pattern in the image. Why do we have different strides? Yes, but you actually this is the hyperparameter. You can adjust it. You can adjust it to 1 or 2, and other, actually in the you can adjust it to, because if you use bigger stride, because if the image is very large, and here, if the image is very large, and this area will be not construct to this object, right? So you will want to take bigger stride to ignore some unuseful information. So, and this kind of so the bigger stride will reduce the size of the feature map, right? So if the stride is bigger, the feature map size will be, the size of the feature map will be smaller, and the calculation will be calculation complexity will be smaller. So that's it. So you can take stride equals to 1, but you can also adjust it. So you can try it. It's a hyperparameter, and you can adjust it to see if the bigger stride will improve the performance, or reduce the calculation time. So this is the convolutional operation, and this kind of filters will detect the loopy pattern in different location of the image.
No, carry on, no worries.
Yeah. So the loopy pattern filter will detect the loopy pattern in the image and in different locations. So for 9, it will detect the loopy pattern in this area, in the top of this image. And for 6, it will detect the loopy pattern in the bottom of at the bottom of this image. And here it will detect 2 loopy pattern, 2 circles, right, in this image. And for 96, it also 2 loopy pattern in different locations. So actually, the filter is nothing but the feature detectors. And for example, in the so actually for the loopy pattern filter, they will detect if there is loopy pattern in the image. For the vertical line filter, it will detect if there is this kind of vertical line in this image. Actually, for we have mentioned that the filter is location invariant because it can detect this kind of feature in different location in the image. So, for example, for the eye detector for the koala example, so it will detect koala's eyes in this image, this 2, and for this different. So for in this image, the eye detector will also detect the eyes of koalas in this area, and also multiple if there are multiple koala's eyes in the image, and it will detect all the eyes of koalas in the image. So we can use different filters, different detectors to see if there is this kind of features in the image, and this kind of filters is very good at detect this kind of features in the image. And for each filter, there will be, after the convolutional operation, the calculation, there will be a feature map the feature map will represent, the feature map is the detection result to see if there is this kind of feature. So for the costing for the handwritten digit recognition task, we have three different filters. So we got 3 different feature maps here. And for the koala detection, the recognition task, we have the eye, nose, ear filters, and then we can go the feature map, 3 different feature maps of that. If there is koala's eyes in the image, and if there is koala's nose in the image, and for this, so after we got these 3 feature maps, actually we can use the higher level filter of the filter of the head to see if there is to aggregate these features to higher level features to see if there is the head of the koala's head in the image. So by the way, the filter can be two-dimension matrix and can also be three-dimension matrix. Yeah. So this is the convolutional neural networks classifier. Actually, this is not the whole framework of convolutional neural networks. We will discuss later. And so in this kind of convolutional neural networks classifier, we first detected the local features like this is very smaller features like eyes, nose, ears, and hands, legs, and then we aggregate these features to higher level features like head, like body, and then we got two feature maps. The feature maps, this feature map represents if there is a koala's head in the image, and this feature map represents that if there is a koala's body in the image, and then we just flatten these two metrics to a one-dimension vector and concatenate these two vectors together. And then we use the full connection layer to predict the label of this, to predict the results. If this is a koala, to predict the label. So in this kind of classifier, there are two parts. The first part is the salient part, and the salient part is actually that is a feature extraction to see in this picture, if there is the koala's head, if there is a koala's body in this image, and then we use this kind of feature maps to make the decision in the classifier layer. This is actually very simple layer. It's just a full connection layer. It will map this vector. Well, it will map the vector to the label space. By the way, the size of this layer is equal to how many labels you have. For example, if this is the handwritten digital recognition task, it will in this layer it will be 10. The size of this layer you will be 10. The results it will be 10 because there will be 10 digit in the label space, right? So actually, this is now the whole framework of convolutional neural networks. So we will introduce the rest of the framework in the framework. So the first one is the activation function. So after the convolution calculation here, this is the convolution calculation we have talked just now, right? And then after it, we will use activation function to help with making the model nonlinear. So model non-linear will help the model to deal with more complex problem. But why this kind of activation functions can make the model nonlinear, and this will need more mathematical knowledge. And if you are interested in this part, you can just Google it, and it will be very interesting, but we won't include this part in our workshop. So we will just to introduce what is this kind of activation function and how to use it. So for ReLU is a kind of activation function. So we can see that this is the ReLU function. We can see for the negative numbers, ReLU will change the negative numbers to 0, right? And for the positive numbers will keep it as itself. So this is the ReLU function. After we apply ReLU function in this feature map, and we will get this result. And then all the negative numbers will be 0, and the positive numbers will keep it self. Is this? So this is the activation function. And another question is, did we address the issue of too much computation in the multi-layer perceptrons? Actually, we did not. We just reduced a little bit. So if the feature size of the size of the feature map is this size, and we have this kind of feature maps, and this feature maps, actually it is also contains very large number of parameters, right? So how to reduce the parameters? So the pooling layer is used to reduce the parameters. So what is the pooling layer? Actually, in pooling layer, we can the two kind of popular pooling method is max pooling and average pooling. So if we have 2x2 filter with stride equals to 2, so for example, for max pooling, in this matrix, we will just keep the max number, and we will just ignore this the other ones. So we will just keep 8 in this matrix here, and we take cause the stride equals 2, right? And we take 2 steps, we move to here, and then we just keep the max number in this matrix 9 here, and then 2 stride here, 3 here, and 2 here. So we then get this feature map. This is the pooling. If we use max pooling, we will use the average of this element in the matrix. So for the 2x2 filter with stride equals to 1, and we can after we use max pooling to this feature map, and we can get this feature map, because here, if the first step is here, and we keep this one here, right? And then we keep this one here, and this here, so we get this feature map. So the question is, because we have ignored some of the elements in the feature map. So will that influence that the detection of the features? Actually, for the actually no, cause the if we have detected this kind of feature, the results of the convolution calculation will be 1. 1 is actually the max number in the matrix, right? So it will keep the results of the detection if there is this kind of feature in the feature map, and it will keep this kind of detection result right here. So it won't change our detection results using max pooling or average pooling. And for the variation problem, if the location of the number has shifted, when we use the activation function and the max pooling, the detection results will not be changed. So we can also see that in the feature map, we also detected the loopy pattern in the feature map in this image. So if we use the average pooling, this is also the 2x2 filter with stride equals to 2, and we will just use the average of these elements. So this average, and average, that we got this feature map. So the benefit of the pooling is that we can reduce the dimension of the calculation and the computational complexity, and then we can reduce overfitting because we just ignored actually many of the parameters. And the model, we will make the model tolerant towards the variations and the distortions. So this is actually the whole construction of the convolutional neural network classifiers. So this is the convolution. In the feature extraction part, the convolution plus the activation function, and then pooling, and then this is one layer convolutional network, and then we connect another layer. So this is the 2-layer convolutional neural networks, and the higher layer will detect higher level features. And then in the classification part, we will use this kind of feature to predict the results, the label of this image. And actually, the beauty of convolutional neural network is that we don't have to handcraft design this kind of features. We can use the propagation algorithm to learn the convolutional neural network learn this kind of features itself. So how we do that? So after we got the prediction, we will calculate the error between the prediction and the label, and then we will use the actually the differential. Sorry, I just forgot the word. Yes, derivation to backpropagate the arrow to the previous layers, and the to update these 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 filters. So use the backpropagation algorithm, the convolutional neural networks will learn this kind of this kind of filters itself. So this is actually the beauty of the convolutional neural network. So before we move to the one-dimension convolutional neural network, so do you have any questions about the two-dimension convolutional neural networks? Okay, if not, okay, how do we decide how much pooling pull by? Yeah, actually, this is also a hyperparameter in the convolutional neural network. So if you want to reduce the computation in very large gap, you can use very large pooling, but the larger pooling may ignore larger elements in the matrix, right? If you use the max pooling in the max pooling. So actually, usually we will use the 2x2 or 3x3, 5x5, or actually it's usually we'll use 3x3 and 5x5 and 7x7. This kind of max pooling, this kind of pooling. And you can try which kind of pooling, the size of pooling filter will improve the performance of the model. So actually in deep learning, like say the convolutional neural networks, there is the huge effort, or a lot of effort will put into adjust the hyperparameters to get the best performance of your model. Actually, you can in deep learning you can search. Actually there are different papers. They have proposed different search algorithms to search the hyperparameters, but we can't. Actually, we from what I know, that we can't just determine the optimal hyperparameters before we run the code, or when we just design the model, we actually can't determine our optimal hyperparameters. So we will try and adjust it, and try, adjust it, try, adjust it. That's it. So any more questions? Actually, for this hyperparameter or optimization, you can. I will let you search better hyperparameters when you are running this kind of when you are running the code. You can adjust. You can change some of the hyperparameters and to see if it can improve or reduce the performance of the model. So if there is no questions, we will move to the one-dimensional convolutional neural networks. So that's how we can use it to deal with sequential data and the text data. So for text data, so I like this movie very much and this punctuation. So for each word, as we mentioned, we can use the word vec to transform this word token I to vector. And here in this example, the dimension of this, the size of the vector is 5. So we got the 7x5 matrix, and we use this whole vector to represent a word. So there will be, this is different from the image. So for image, we have local, we have to detect the local features. So we will move the filter along the 2 dimension of the image, this way and this way. But in image, but in the text data, so the sequential data, we will just move the filter along the sequence. So here the difference between two dimension convolutional neural network and the 1-dimension convolutional neural networks is this. In the two dimension sense, we will move the filters along the 2 dimension of the matrix, and in 1-dimension sense, we will just move the filter along the sequence. So, for example, if there are 3 different sizes of the filters, and there will be 2 filters of each size of the filter. So totally is 6 filters. So, for example, this is the size 4 is actually how many words or how many tokens will be covered in this filter. So under along this dimension, the size of this filter will equal to the size of the embedding vector of the word. So here is 5, and the filter will be 4x5. And if the embedding that the vector size of the word token be like 128, the size of the filter will be 4x128. If the size of the word vector to be 300, and the filter will also be 4x300. So the first, we will use this filter to to actually after that it will be sent to the two-dimension convolutional neural network. So we will use filter to do convolutional operation calculation with this filter. With the filter will cover this area, right? The first four tokens. And then we got this result, this number. And then if the stride equals to 1, and then we move we will move one step. And it's 1, 2, 3, 4. Yeah, this matrix. And then we got the second value. And then we move another step. This matrix. And then we got this value. And the last step and last value. And for this is the feature map. The feature map of one dimension convolutional network is one dimension, right? And then the feature map of two-dimension convolutional neural network is two dimension, right? And then we use pooling, max pooling. Max pooling we will just keep one of the max number in this feature map and one max number in this feature map and concatenate. And for this two, and we can see that one feature map or one filter will have one feature map, and the one feature map we will just keep one number. So after that, the representation we will concatenate these 6 numbers together as the representation of the sentence. So we can say that the size of the representation of the sentence is equal to the number of the filters, right? Because one filter will have one feature map. The one feature map we will just keep the max number. So we will have the six numbers here to represent as the sentence representation. And then we can use this sentence feature to predict the label of the sentence. If in our example project, the sentiment classification, it will be positive or negative. So do you have any question for the one-dimension convolutional neural network? So this is how we use the convolutional neural network to deal with sequential data, to extract text features. Okay, no, right? So after we have talked about how to represent the word, we use word embedding, word web, right? And we also talked about how to extract sentence representation using deep learning framework like convolutional neural networks. And then how can we use it in your project or in our project? And what is the structure of the deep learning system? And how many steps, which steps we will take to construct this kind of deep learning project. So generally, for a deep learning system, there will be three parts. First part is the data pre-processing part. No matter for computer vision or NLP, for image data or text data, there will be data pre-processing. And in the data pre-processing pre-processing part, there will be three functions. Actually, for different data, for more complexity data, you will have more functions to deal with your data. So this is a broad workflow, and will be reader to read the data, to load the data, and the cleaner to clean the data, and the tokenizer. The tokenizer will split the sequential data, like the sentence, to words, like, and punctuations, like here. Here, I like this movie very much, and this punctuation. This and how the size of the sequence, the size of the metric is determined by the tokenizer. So if we use n-gram character tokenizer, like for example 2 gram. So the first token will be I and a space. Because in English, we use space to split the words, right? So if we use 2 gram character tokenizer, the first token will be I and a space, and the second will be space and L. The third will be L and I, and KE. So the size of the matrix will be determined by the tokenizer. And in this project, we just use word token. So we just split the sentence by the space. So and we will use for English there are tokenizers, and we can use the libraries to the packages to tokenize the sentence very easily. So the second part is the model part. Actually, this will be the main part, the core part of our deep learning project. So in the model part, there will be two subparts, and one is the construction, and one is the data flow. Construction means how you build this model and the construction of your model. And for example, for convolutional neural networks, we will have convolutional. Actually, there will be an embedding layer, embedding and the convolution and the pooling, activation function, and the activation layer. And the data flow will determine how your data and will flow in your model, and the calculations in the data that's in your model. Because actually is that the interactions between your these constructions, this component in your model. And after we have this kind of, after we have data, we have model, and we will determine we have the controller part. Actually, this is the controller. training, and the data loader will control the input of the model, and the trainer will determine the training process of your model, and the evaluator will evaluate the performance of your system after we have trained, and we have trained the model, and the evaluator will also help us to select the best form model and we will save the parameters, save the whole model, and then when we want to use it for prediction, for testing, we will just load the whole model. And actually, I will show you the data flow of the convolutional neural network. So after this, after we have a clear image in our mind of the data flow of convolutional neural network, it will be very easy for us to write the code. We'll just step by step write the code. That's it. So if we have a sentence, and it have L words, and the length of the sequence is L, and then we can use the embedding matrix to get the representation of each word, and the embedding size of each word is M. So we can give a L by M matrix, right? And then we will use the CNN network to extract the sentence representation, and then we got a 1 by n vector to represent the sentence. It's like this here, right? And then we use this vector to predict the label. And in this CNN, we will have different filters. So there will be k for this size of filter, the D by M filter, there will be k this kind of filter, and then we have said that one filter will have one feature map, right? So we have k feature map, then we will have k feature map here, and if the stride equals to 1, and the size of this feature map will be L minus D plus 1, right? And then we will apply max pooling to keep the max number in this feature map, and each filter will just have one number, and so we concatenate these numbers, we will get 1 by k vector, right? And then if we have different size of the filters, so for example, if we have two different size of the filter, so we have 2k filters, right? And then we will the same as this, we will get another 1 by k vector, and then we can concatenate this two vector. It will be 1 by 2k vector, and we will use this kind of representation. Is this sentence representation to predict the label of the sentence. So do you have any questions about the data flow? Okay, so if not, so next part is the, I will show you the code. Yeah, in this part, I will show you the code. So let me check if this is connected. Okay, so so actually I will send you the notebook later, and you will try to run this to Python notebook afterwards. And if you have any questions, you can Google it first. Actually, you know, in my experience, you Google is my best friend. And if you have any questions, you can Google it. And there will be, you know, when you use this kind of deep learning framework, the other people may encounter the same problem as you, and you can search it, Google it, and you may get the answer. If you cannot solve the problem you have, and you can ask us, that means Mingshan, Daniel, and we are glad to help you to solve the problem. And so, as we mentioned in the workflow and the data flow, so we will construct our code first. So the first part is the data processing part. So we will first look at the data format, and actually this data is the same as the data used in our last session, the ML, the decision tree project. And this is the text, this is the ID, and this is the tag, the sentences, and this is the label. So if the target is 0, the label is negative, and if the target is 4 and the target is positive, so this is the data. So we just load the data. So here is the libraries we need, and this is the hyperparameters we have, and so first we load the data. Actually, this is easy for you to load the data, and the data has two parts. The first one is the text part, is the sentences, and the second one is the labels. So let me run this. So after we read it, we can check if the data is the same as what in your mind. So here we think that in this list, in this text list, there will be multiple sentences, right? And in the label, we will in the label list, it will be the labels. By the way, the labels should started from 0. So if you have if you have two classes like negative and positive, the labels will be 0 and 1. And if you have multiple classes like 5, so the labels will be 0, 1, 2, 3, 4. This is 5. So the labels must have to started started with 0. So we just the best way to check if the data in your code is correct, you can just print it and to see if it is correct. So here it's correct, and actually we can output the last. It's ones, right? And then after we load the data, we will clean the data. Actually, the cleaning of the data, we have the Minshan has talked about the cleaning of the data in our last session. So we won't repeat the cleaning process here. So we will just skip this. And if you have any question, you can rewatch the video of our last session or look at the notebook of our last session. And then is the word tokenization. So we will use the library from NLTK and the word tokenize function to split the sequence to word sequence. So this is so actually we can show you an example. Sorry. Let me check. So, oh, yes, you really split me. So, we can say that we have split the first sentence to the words, right? So this is the results of our tokenization. And then, because we will transform the word to vectors. So we will have to know how many words in the vocabulary. So we will just here is the dict, and we will count one word has show how many times in this corpus, and then we can choose we can keep all the words in the corpus as the vocabulary, but actually we don't have to. We can do, but this will increase the size of your embedding matrix. So that should usually we will keep the most frequency words. So the first 3,000 words in the corpus as the vocabulary. So this is the we just put all the words in this dict, and this dictionary will record the frequency of each word in the corpus, and then we just keep the first most common the first 3,000 common words in the corpus and as the vocabulary. So so here we got we got this kind of dictionary, and here this is the word and this is the index this is the index of the word. So we will use this kind of index to search the vector of this word in the embedding matrix. So why the index starts from 1, not from 0. I will talk this later. And then after we, because the computer cannot process the word directly, so we will change the word to its index, its ID. So we will have this function, word to ID. So we will use this dictionary to change the word to IDs. So here, this is the function, and here. So here, for example, for the first sentence, and we will change the word to IDs. Actually, his ID, or the ID of I is 1, right? Here. So this is the word to ID. And I just mentioned that the index started from 1 now instead of 0, because we have to padding. So why do we need padding the sentences? So padding is we will cause the length of the sentences is different. But if we employ the batch training, that means we will process multiple sentences at the same time. So we have to make sure that in the same batch, the size, the length of the sentences is the same. So this is why we will use the padding. So for padding, for padding, we will have the length, the sequence length. This hyperparameter, we will determine the max length of the sequence. If the sequence is longer than the max length, we will cut off it. We will cut off it to fit the max length. And if the size of the sequence is shorter than the max length, and we will pad it. We will pad in zeros, usually zeros. Actually, if you want it to be 100, it also can. And usually we will pad 0. So we will put the pad zeros in the from the end of the sequence to fit the max length. So here, if the length of the text is shorter than the max length, then we will pad the zeros to match the max length. And if the length of the text is shorter than the max length, and we will just cut off it. So this is and then we will make it a matrix. So for example, see the max length here is, for our project, is 50. So we can see here, in the end of the list, we just pad zeros to the list, right? And then we will split, because in this data set, we don't have the data has not split to train and test eventually. So we have to use we will have to split the data to training data and test data. So here we just use the function from the this packet, Skinner packet, to split the data. And sorry, one wrong. Let me check, because we want to keep the random state consistency. Yeah. So after this, we will split the training data, including the texts and the labels. So here is the so the test size is the percentage of the test set in the whole data set. Where here is we set 0.2, so the length of training data is 8,000, and the length of test data is 2,000. So after we have finished the data pre-processing, we can start to construct our model. So as we have shown you that in convolutional neural network, there are three main components. Is the convolution, the activation function and pooling, and also including the embedding matrix. Embedding matrix, the embedding of the words in the vocabulary, right? So there are four main components. So here, so first we will have this embedding, the embedding layer. So if you want to know how to how to construct the how to use this function in PyTorch, you can Google it. Here we just show you the code in our project. So here you can just simply use this function with several values. The first value is the vocabulary size. This is the size. These two values will determine the embedding matrix size. So the size of the embedding matrix is the vocabulary, how many words in the vocabulary. So here we have the vocabulary size +1. So why +1? Because we have a padding, right? We have a padding token in that is 0. And the embedding size, the embedding size, the size of the word vector. Here we have so we have shown here we use 128 as the word vector size, and then it's the convolution layer, right? So here we will determine the size of the kernels, and here we use three kinds of size, 2, 3, 5, and 4. And for each size of the filter, we have 100 filters. So how many filters we have in total? It's 400, right? Because for each size of the kernel, the filter, we have 100, and we have 4 size of kernels, and we have 4 different size of filters. So we have 400 filters in total. So we will use this function to make a list of these convolutional layers, and we will the in channel is the dimension is the word embedding dimension, because here we just the kernel size will just because the filter is a 2-dimension metric, so this one will just determine 1 dimension of the kernel of the filter, right? And this embedding we have mentioned before, the one of the dimension of the filter is equal to the word embedding size. So here, this will determine these two will determine the size of the kernel, and then this will determine how many kernels we have. Then after that is the activation function, right? And the pooling. Actually, these two we will put in the forward function. So the forward function will determine the data flow in your model. So this initial function will construct the component you have in your model, and the forward function will determine the data flow in your model. So and the dropout is we will mask some of the element in the feature map to deal with the overfitting problem. And the connection layer is actually the classification part we have mentioned in the convolutional neural network classifier. So the data flow is here. So this is the input. The input is actually so I can show you so we can just print it. Oh yeah, we have to let's expect it 0 and 2. not enough. Here. So, so we can see that the size of the input is 32 by 50, right? And so that this, because we use batch training, so there are what are the meaning of these numbers? So there are 32 sentences in this batch, and each sentences has 50 tokens. The length of each sentence is 50 because after we padding it, right? So after that, we will, because this is still the sentence, the input. So after that, we will change we will transfer the words to vectors through this word embedding, right? So we just use this to change it. So here we can put the size of this. So as we mentioned, we can just mask this, comment this first. So we mentioned that the embedding size of the word embedding size is 120 and 28, right? So there are 32 sentences in the batch, and the length is 50, and the size of each word embedding is 128. So why we will transpose these two dimension, because we use one dimension convolutional neural network, and the filters will move along the last dimension. So we will transpose, because as we mentioned, the filter, okay, here, not here. Sorry. As we mentioned, here, the filters will move along this side, right? So after this, we will transpose this two dimension to let the filters move along the sequence dimension. And then after this, we will this is the convolution. So after convolution, what is the size? So to make it simple, we will just have one size of the filter. So it's 2, right? 2 by 128. So what will be the size of the feature map? So it should be here. We have 100. Okay, the size we have talked is here. So if the here is 2, the size of the feature map will be 1 by L. The L is 50, right? 50 minus 2 plus 1 it should be 49, and there have how many this kind of feature map? 100, right? So it should be the size of the output should be 30, 32, 100, and 40 and 49, right? So let us check. Because this is a list, right? Here, right? And then we will use max pooling. So after max pooling, so for each, this is the feature, the size of the feature map, right? And then we will keep one max number in the feature map. So this will only one number remain. So the size of the output after max pooling will be 32 by 100, right? Okay, let me check. Let's check the size of this output. Right? And then we will calculate, because if we have different kinds of different sizes of filters, so we will calculate this kind of feature maps together. So if we have 4 different sizes of filters, so if we have this way, right? And after we can calculate these feature maps, it will be the size of the output should be 32 by 400, right? Here. And then we will map the feature map. This is the 400 vector is the representation of the sentence. So after that, we will predict the label of the sentence. Use this full connected layer. So the output of the full connection layer is the size of the label space. Here is 2. How much labels we have? We have 2 labels, right? It's negative and positive. So after this, after that, we use the softmax to transfer it to calculate the probability of the sentence to be negative and positive. Here is the output. So for the first instance, it has like 33% to be negative, and 66% to be positive. So this is the whole network, the whole model of our text CNN, right? Here, so this is the data flow. So the forward function will determine the data flow of in your model. And if you have as I mentioned before, if you have a very clear image, if you have a very clear data flow in your mind, you can just write the model, code the model very easily, right? So for starters, it is hard because you are not familiar to the PyTorch framework. After you practice it, it will be easier and easier. So the last part is the control part. Is the data loader, trainer, and the evaluator, right? So we will use here. We will use the torch functions, data set and data loader. First, we will map the text and labels together. And then the data loader, we just put the data and the batch size to the data loader. The data loader will feedback that will return the batches, different batches of the training data and the test data. This is a very convenient function, right? It is very easy to use, and you don't. But for in other complex projects, you may have to construct your own data loader yourself. So after you explore more in this area, you will find out. So the next part is the training part. In the training function, this training function will control the training process of the model. So here this is the data loader part, and we will define the optimizer to, as we said, the beauty of convolutional neural network is we can use propagation algorithm to update the parameters and to learn to make the filters itself. So this is the optimizer, and we use the Adam optimizer here. And it's the loss function. The loss function is to calculate the error between the prediction and the label. So the cross entropy loss is very common used in the classification tasks. So this is actually how many epochs we have, and then we just train the model batch by batch, and we first have to set the gradient of the optimizer to be 0, and then we use the model to get the prediction. Here, the prediction is we have just shown you the probability of the sentence to be negative or positive, right? And then we can use the prediction and the label. Why batch is the label of this batch, and to use the function to calculate those, and then we use the back propagation algorithm to update to calculate those and to update the parameters in the model, and then and we can save the predictions. And after we save the prediction, we can use the evaluation part to see the accuracy of the training dataset, and then we can also use here use the calculate of accuracy to see the accuracy of training on training set, and we can evaluate the model in the training set. So this is the evaluation function. Actually, evaluation function is very simple, and we have set the model to evaluation, and there will be no gradient and no updating of the parameters. So it is very easy. We will use the model to predict the label of the test samples, and then we will use then after we get the predictions, we will use this calculated accuracy function to get the accuracy, right? This function is very easy, right? So after this, we can train the model. So I will show you the training process. Sorry. Let me check. Print. Here. Okay. So we will train we will train the model for 20 epochs. Here you can see this is the training accuracy, and this is the test accuracy, and this is the loss of your model. And we can see, I remember that for this data set, the accuracy for decision tree is about 65, right? And if we use convolutional neural network, we can got the best. I think the best is here, right? We can almost get 74% accuracy. So this is the I will upload the notebook later, and you can try this code on our pandas classification task later, and you can your task, you have 2 tasks actually. Actually, it's 3 tasks. The first task is to use this notebook to run the code on pandas classification task, and then, as we mentioned before, the word to vec here. Here, the embedding, the embedding is just randomly initialed word embeddings, and your task is how to use the pre-trained word embeddings like glove in your project. And actually, it is not very difficult, but you have to Google it and to find out how to use it. And the third task is you have to change the parameters in this model, not only in this class, but also in the model, like these parameters, and to see the influence of these parameters, and when you change it, how the accuracy changes. So this is your tasks. So next part, the Rabiul will talk about the recurrent neural networks. So that's all. That's all for my part. Okay, thank you. It's time for Rabiul.
I think before we move on, right? Why don't we just take a short 3 minutes break? Then we come back at, let's say, 11:15. Yeah.
Yeah, sure.
Yeah. So perhaps you guys can take a short break. Then we come back at 11:15 to talk more, right? To share about. I think what's coming up is we're going to share about RNN, right, Rabiul?
Yes.
Yeah.
We can.
RNN and LSTM.
Yeah. And if you have any questions, you can ask.
Yeah, hi everyone. This is Rabiul, and welcome second session of micro machine learning and deep learning workshop. Okay, so in my section, I will talk about mostly recurrent neural networks. And we already discussed some parts of like how can we model sequences using convolutional neural network. I will talk about a different kind of network that has recurrence in its design. And we will also talk about when we model sequences, there is a problem arises called long-term dependency. And for that, we have a special network, which is called long short-term memory networks. And then eventually, after discussing these two building blocks for working with sequences, we will move on to classification task and work on Jupyter Notebook. Okay. So sequences in our day-to-day problems, there is a lot of stuff that involves sequence. And let's say speech recognition, if you have an audio, like at the moment I'm talking about, all of these comes as a sequence, one after another. And then if you have, let's say, visual question answering, let's say you have an image and you are going to ask a question about that image. And then the answer need to be in a sequence. And if you want to create an AI for generating poems, then also requires a sequential generation of each tokens, like each words, right? And then if you are thinking about maybe generating some C codes, and I guess some of you may have heard of GitHub Copilot, that kind of stuff also requires sequence generation. So, and sequence generation or understanding sequence, that means that there is something going on about the word appearing in a particular order. And we are looking for networks that can work with sequential order of sentences and documents. Okay, so recurrent neural networks are theoretically mainly developed for these kind of problems that involves sequence handling or modeling sequences. And it's not much different from the network that we have seen earlier, like neural networks, which is standard neural networks or convolutional neural networks. Convolution has a specific property on its with convolution, but with a standard neural network that has input layer and some hidden layers and then output layer, recurrent neural networks also has the same structure, like input, hidden, and output layers. So recurrent neural networks are also deep neural networks. So essentially they have the somewhat more those properties. The only difference between standard or vanilla neural networks and recurrent neural networks is the word or term recurrent. So here, each node or each neuron pass some information to its neighboring neurons. And we'll talk about how they do it and why we care about this kind of message passing to one neuron to another neuron in a sequential manner. Okay, so you can think of recurrent neural network something like multiple copies of neural network. And let's say here we have A as a neural network and X is our input. And we have X as input and we send it to neural network A and it gives us an output. But you have multiple copies of A and each network has a feedback loop. So and then this feedback loop is something like it's recurrent, as you can see in the image. So, and what's going on here, output at current time step depends on the previous step and by recurrent edges. And we'll look at it, how do you mean by that output at current time step depends on previous time step. So this is, if you go for any textbook on recurrent neural networks, then you will find and maybe a diagram like this, where they call it unrolled recurrent neural network. So we have a recurrent network, we have some feedback loops here, and if we unroll it, then it explains what's going on here. So we have an input X and we send it to network A and it gives an output H. And let's say this is happening at time step 0. Then we go on time step 1 and we have a on time step one, maybe you have the second input and then you send it to network and it gives us output. Now, this is something really interesting here, that when we are working with time step one, there is an arrow from time step 0. So you can see 0 and A0 and A1 has a connection. So there is an arrow from network A to network 1. So, and for all of them, we have to see that there is a connection, that each time step gives some input or feedback to its next time step. So this is what we call like a feedback loop in the network. That you, so let's just think of an input sentence, like I go to university. So this is your first time step, and then you process it with your neural network. That's easy. That you have already learned about how to process something with neural network. And then after processing, the hidden states, we send it to the next step, which is, let's say, go. So go is your next word that you are going to process. You plan to process it. And while you're processing it, you have a feedback from your previous step. And then if you go to 2, then 2 also has a feedback from its previous step. And university also has a feedback from its 2. So it's like, it's a sequential order, you get the feedback. And definitely it looks like a chain. And what's going on here is network or each copy send a message to its neighboring copy. And this is how the chain grows. Now, this is the only thing that we should care about recurrent neural networks, that you have a feedback loop, and it looks like a chain growing through the timestamp. And the most critical component is the consideration of timestamp, that we start from timestamp 0 and then we go for timestamp 1, 2, 3 sequentially by maintaining a proper order. So we don't do it something like we start from 0 and we jump to sequence 4. That's not going to happen. What's happened here, we start from 0, then we go to next 1, next 2, 3, and time step T, which is our last time step. Okay. So, so something got messed, but I can explain. So we have an input X, and then we have a network A. There is something going on inside neural networks, lots of neurons, all that stuff. Then eventually we have output H. And whatever happening in the middle, we call it intermediate state. And that intermediate state is called HT, which you know by now that is called hidden states. So we have a X as an input, H as a hidden state, and output. So we got the output, right? Now what's going on here, if we look at the equation, so we already in our first session, we discussed that neural networks are just some function approximators. So here HT equal to F, some function, it takes some input. Now this input is something that defines the recurrence property. So typically for other neural networks, which is a standard neural networks, you have input X and some parameter theta. And that's for all kinds of neural networks, you have this. You have some input and some parameter for representing that network. Now in recurrent neural network, we also have additional input, which is HT minus 1. So this is like you are working with time step T and you have an input for that time step XT, and you also have this additional input from previous state T minus 1, and its hidden state is given as an input. So simply we can write this, we can just, this is an equation, and eventually if we just go further in this equation, we will have some W and U and B, you know, these are weights and biases. And eventually we take that output HT and send it to a classification layer. We'll see. So I guess by now from the discussion from convolution neural network, so eventually after processing steps from hidden layers, we want to also have a classification layer, which takes the output from hidden states and produces an output. Okay. So there are many kinds of recurrent neural network exist, and it depends on which problem you are trying to solve. So very simple one would be one-to-one connection, that you have a one input and you just expect to have one output. So then there are other, like you have one input and you want to have that produces multiple outputs. So one-to-many. So it is something like, would it be, let's say that you have a network and you give it a topic. Let's say topic is a sport. And so you have only one input, that is a sport. And then this is a sequential generation network, right? Recurrent networks can generate stuff in a sequential manner. So what you are expecting now to generate a couple of sentences on this topic, let's say sport. So here we have only one input, sport, but the network will produce a list of maybe 3 or 4 sentences and write some stuff about a sport, that is sport, there is different kind of sports and all that, blah, blah, blah. Let's say some documents or some paragraph on that topic. And then this is one kind of problem that you would be interested in. Like I have a topic and I want a network to produce just a bunch of sentences about that topic. So one input, but output are many of them. Then there are problems that we work on in our lab that has many-to-one connection. So let's say there is a problem on hate speech classification. So we have a tweet, a post from Twitter. It has maybe 280 characters. And so let's say you have many inputs, which is 280 characters. And then you want to just get a classification output. That is it hateful or not hateful? Then we have many inputs, but only one output. Is it either false or is it either true, hateful or not? Then there are other problems that we try to solve in NLP, language processing, that involves many-to-many network. So it's just a choice in designing and the problem space. So many-to-many will be something like for sentence, let's say we are given an input sentence, we want to measure the hate intensity for each token, that which word makes it highly hateful, that kind of problem. So in that, if we want to make prediction against each input, so let's say there is an input sentence given and we have 3 words in it and we want to measure what is the intensity of each of the word in that sentence. So that would be many-to-many. Okay, that's recurrent neural networks. And so we mostly use, I mean, if you are working on early NLP problems, then you might be aware of, or you might be introduced to many-to-one situations where you have an input sentence and you want to just make a prediction on that input sentence. And that prediction just need only 1 neurons. Okay, so recurrent neural networks, whole idea based on this intuition that we need to maintain word order, and word order matters while we try to process any sentence or any document, or maybe some audio or other stuff. So why we can't, so the question is pretty simple. Can we use neural networks, standard neural networks, and solve this problem? Why we need recurrence? And like already we have had a discussion about convolutional neural networks. They do not have any recurrence, but you can solve NLP problems using convolutional neural networks. So why do you care about this recurrent neural network? The reason is human language has a sequence in its, I think all language has a sequential property. And when we speak, we speak in a maintaining a word order. So here is an example. I go to sleep, and if I just scramble this and just permute its position, then you see, let's say I have a sentence which say, sleep to I go. Now, this doesn't make sense, right? If you are reading this sentence in this manner, it's hard to read this sentence. And if I give you an article where all the words are just scrambled and they change their position, then it's very hard for you to make sense of that document. So now in standard neural network, we don't have this sequential property that processing goes on, or we don't have word orders. They don't take into word order in their processing or in their design. So recurrent neural networks have this word order and sequential property. And so as language is sequential, recurrence help us to understand language better. And it also, if you think of the message passing, it builds up something called context. So at each time step, we process one token and we go further. But as we go further, I mean, I go to, after two, there should be a verb, right? I go to sleep, I go to university, I go to some pizza shop, something like that. I go to somewhere. So after I go to the number of tokens that you can fill here, if I give you a blank space, I go to, then after that it's just a blank space, then you have some options and limited options, because after go to, I can say I go to go. That doesn't make sense. So when we process a sentence in a sequential manner, it also helps us to constrain the problem space and also develop the sense of context in our language processing. That's why we are working with these neural networks. Now, in this discussion, we mainly interested in how to train them. You understand them, they are not really complex. They just have this feedback loop that one time step sends an input to its next step, right? So it's pretty simple, but the complexity arises when you try to train them. So standard neural network training uses backpropagation. By now, you must be aware of that. And so how backpropagation will work for deep neural network? So usually what happens, we have so forward propagation starts from your first layer, that is input layer. Then we go that process the hidden states, and then eventually it processes the final output layer. Then the back propagation starts from the final output layer, and it follows the backward, like then it goes to intermediate layers, then it finally process the first layer, which is input layer. Now, there is something that is interesting, that we have we have x0, x1, x2, xt. We have, let's say, these time steps, and each time step we have we send an input and it process some hidden states, and we get some error from that state. Then next state we also get some error, and after that we get some error. So each time step has an error. So if you want to calculate the error, we just need to calculate the all time steps. That's not complex, that's pretty easy. That we have 10 steps, so we are just taking the sum of all those 10 steps. So error computation is not really complex, but the complexity arises when you think of backpropagation for each of the state. Now this is something really interesting. Now let's look at one step. Like when we think of backward, we will process first ET, our T time step. Now T time step, when you think of processing T time step, we need to remember that we had some input from its previous time step, which is T minus 1. Let's say we had input from H2. Now you are trying to compute HT, but the problem arises, you also need to think about H2. Then, okay, let's say we want to compute now H2. That because we need H2 to compute HT. So you think of, okay, let's first compute H2 first. Then when you think of H2 also has a connection from H1. Then you need to now compute H1. Then when you think of, okay, let's compute H1 first. Then after H1 also has a connection from H0. So it seems like there is a flow of gradients or information, because as we build the connection in a sequential order, as we are trying to flow the information forward, then the error propagation or back propagation will also pass the information backward. And when we are trying to calculate ET here, we need to go to ET minus 1. So this is something pretty makes the work a little bit harder compared to other kind of neural network, because if you think of this chain is pretty long, let's say you have 1,000 tokens or 1,000 time step, then maybe computing 900 time step, you need to go back to a 0 to 900, something like that. So that's really a huge chain, and you are passing your backpropagation information in that huge chain. So what could go wrong in this kind of long chain of information processing? Or if you think of just passing gradients in this long chain, what could go wrong? What are the difficulties that may arise? Any thoughts over that? Anyone has an idea what could go wrong if we try to process the last step, and we realize that, okay, processing last steps requires a connection to its previous state, then that state also has a connection to its previous state. And eventually you see that there is a whole chain from first step to last step. What could go wrong in a computational perspective? Any thoughts about this? Okay, I'm trying to get some feedback from participants. You can try anything. It could be wrong. It's okay. And so gradient vanishes. How do you mean gradient vanishes? What does it mean that gradient vanishes? You can try wrong answer. That's not a problem. Okay, so repeated multiplications, it becomes too small. Yeah, because that is one problem. Yes, exactly. You have, let's say at error, we have 0.00001, very small number of floating point. Then this information, we are passing it to its previous step. Then then that also has a very small number. Then eventually, if you keep multiplying a set of small numbers, the ultimate value will be 0, like, or nearly 0. So that means that there is no gradient. And if you don't have any gradient, you can't train a network. I mean, what is the derivative of 0? It's just, so if you have a 0 gradient, then eventually, if you have a 0 error, then eventually you can't, I mean, train the network or pass or make the weight understand what's going on inside the network. So that is one problem that we have. So it could be in either way, that you have a small value and you multiply it a couple of times, or in a long chain you keep multiplying it and then it vanishes. Or it could be opposite, that you have very big value and a large number and you keep multiplying that number and it becomes, it explodes the whole computation. So that could be either of them. So either it is a very small value or it is a very large value. If you keep multiplying them, then eventually either it explodes or vanishes. Okay, that is one problem we understand. What else? It has to deal with basic computer science, computational perspective. There is another problem. Okay, so the second problem could be something like, problem is that you have to always rely on this sequential processing. There is no way we can parallelize this computation. So we can say something like, let's say I have 100 sequences. I will compute first, train first, and maybe some 20 to 30 later, or 30 to 50 in other processor. It's not something like that. You have multiple processors and you just split your task and send them to multiple processors. That's not possible because there is a sequential requirement. It's not parallel. We can't do parallel computation because there is a dependency between each time step. So we can do that. Now that also creates another problem, which is the computation is pretty slow. So as we can't do try this parallel computation, we have to do sequential, and it takes a lot of time to process it. Okay. So the technique that we use in training neural networks, that is called backpropagation, and it has a short name called BPTT, which is backpropagation through time. So the idea here is we start from time step T and then we go backward. So first we go forward, that's what the line, forward line. Then we go backward, forward and backward. Forward propagations just compute the loss, then we backward through entire sequences to compute gradient. Okay, so this is the common to all the neural networks stuff. You have a forward step and you have a backward step. In forward, we compute loss, and then backward, we just compute the gradient. Now, the problem here is we have lots of sequences, and that means too many terms, gradient terms, and we want to multiply them. And that's a computationally expensive operation because you can't do the parallel processing here. We have to do sequential processing. And as we are doing this sequential processing, it also becomes a bit slow. Now, what can we do to solve this problem? That we have too many terms that we are multiplying. Maybe we can, because we have each time step, so we can't do anything about that terms, because each token has one term. So that is obvious. Can we solve the slow problem? Any idea on how to make it faster a little bit? Okay, this is kind of practical tips that really has no theoretical grounding. It's just a very practical training scenario circumstance. So most of the neural network literature is not really something that is based on a lot of theory. It just people tried a lot of engineering hacks and some of them worked, and then eventually theory was developed to back those practices. The one very naive practice in this kind of training is to, let's say we have 100 tokens here. So what we are going to do, we will split the network, let's say in 3 parts, and we process them each part separately. So you take each component chunk and just compute the loss and then update the gradient, and then we go for another chunk and do it. So it is something like, this is called truncated backpropagation through time. So we truncate in multiple chunks, and then we compute the loss and do the gradient, and then we do it for all the separate chunks. So now you solve this, you can introduce this parallelization concept, because let's say we have 100 sequences, we separate three chunks there from there, and then each processor processes one chunk, and then we compute them separately. Now it also, it is faster. You don't have too many terms because now you already divided by 3. Then you reduce number of terms in the computation. So it also lightly solves the exploding or vanishing gradient problems. It does not solve the problem in total. All the problems are not solved, but it gives us some trainability in the network. Okay, now there is one problem that also arises with these circumstances. So what we are doing here, we are splitting the network into 3 parts or 4 parts, or whatever our engineering hack is. We are just dividing it in multiple parts, and we are thinking that we will compute loss or gradient for each part separately. That means that you are ignoring all the dependency that is involved in other parts, because there was always a connection among all of them. So sequential connection. Now, when we separate it out, it means the connection is gone. That means that you don't have the long-term, you don't have the dependency. So if we start from position 0 and we go to position 100, that means you have a long-term dependency. And that long-term dependency gives you exploding gradient or vanishing gradient. To solve that problem, we just think about, we will split it out. But when we try to split it out, that also doesn't really give us the dependency. It just gives us training techniques for recurrent neural networks, but it does not really solve the long-term dependency problem. So how can we handle long-term dependency? Because long-term dependency matters in a lot of problems. Like if I say something, I go to university, I met Kale, and then I talk with Jacob, and Jacob offered me some ice cream. He was very happy. Now this he can be Kale or Jacob, something like that. You have a long dependency. And then I ask a question, where do I go? Then you have to come to my first sentence where I say, talk about I go to university. So the problem is something like we start with some story, and the story grows in a dependency, and you process all the long story. Then eventually, as we are, what happens when you have a vanishing gradient or exploding gradient problem? The intuition is what you have processed earlier, you forget them. So you can't handle the long-term dependency. You can't remember what you have processed in the earlier step. Those you forget it. So this is a very real world problem, because most of the documents that we were working with, they have a long dependency. If you can think of, let's say, a news article, that has a lot of dependency, right? Because it talks about a long story, and now it doesn't help us. Great. Now we want to solve this long-term dependency problem. That means that we realize that in recall neural network, we have a long-term dependency, but the problem is it suffers from this vanishing or exploding gradient, which is just you have a small value in those gradients, and if you multiply all of them together, then it becomes 0 or it becomes infinitely large number, and that doesn't really help. So we also tried this truncated backpropagation, which is to split the network into multiple parts and do the backpropagation in that manner. But that means that we are leaving the dependency thing just from our training criteria. That also doesn't help. It's a solution of trainability, but it's not a real, it doesn't give us long-term dependency at the end. So we are looking for something that can give us long-term dependency. And as I said earlier, that it's just a case that if you have a very small value, you multiply it and the gap grows, it becomes 0, and the connection doesn't matter anymore. So if it becomes 0, then the connection doesn't matter. So we are looking for something that can give us. So it could be, again, infinitely large. It could be infinitely 0, very small value. And if it is infinitely large, that called exploding gradient. And if it is infinitely, it is very small value, that called vanishing gradients. And so how can we solve this? How can we solve this exploding or vanishing gradient problem? So there is again another engineering trick that is pretty simple to think about. It's just a very, very simple idea that we clip the gradient. So what is happening? The problem is you are computing at some time step, and you see, oh, my gradient becomes very large. And if I pass this gradient to next step, then maybe it will eventually ruin my whole learning process. It will eventually make all the gradients to 0 or infinitely large. So what we can do, we can clip the gradient. Something like if you have a very large gradient from one time step, then you clip it and you keep it small, so that it doesn't grow exponentially large. So in that settings, we solve the exploding gradient problem. So this is a very, very simple technique. You just need to write one line of Python code. So we have a time step t, we compute our gradient and we see it's become large. And let's say we said, okay, if it is become greater than 1.5, it's an imaginary number, 1.5, then it's too large for us. So you just want to make it 0.9 or 0.5. That's our choice. That's a training choice. So by doing so, what we are trying to do here is we avoid this exploding gradient problem. So this is one of the successful idea in training neural networks. So we have two ideas. One is truncated backpropagation that sometimes works, and you can also try this in gradient clipping. And if you are training maybe in your code, it is somewhere in the hidden, you don't know maybe, but it is there. If you open up the code and look at all those Python stuff inside, then you will see there is gradient clipping in that code base. Okay, now that is whole idea of doing this recurrent network in practice and trying to do it as much as we can by doing gradient clipping or truncated backpropagation. But the problem is still it doesn't help much, because gradient clipping solves the problem, but still it is not really give you 100% solution. To get the much more better solution, there is a new kind of network that is used in practice, which is called long short-term memory network. Okay, it was invented by Schmidhuber and Sepp Hockrider. And if you belong in AI community, you will learn about Schmidhuber for a long time. He has a lot of like revolutionary idea in deep learning or machine learning. So the problem here is we have a vanishing gradient problem. And so what we are trying to, what they say to solve this problem or introduce this idea, memory cell. So the idea here is each time step will also have a small memory, and a memory with some input and output, with some read and write operation. So in recurrent neural network, we have seen that we have multiple steps, and just think of each step also has a memory, or each of those copy has its own memory now. Now, giving a memory is something fun, because then you can store your own stuff there, and you can just store it. And so memory has something interesting in the sense that if I have a memory, I can think of two ways that I can erase what in that memory available, and I can write new stuff there. So, and how much stuff you want to write, then you can also decide on that. Or how much you want to forget, you can also decide on that. Let's say we have a memory. So a memory always gives you this kind of reading and writing operation, which we will expand later on from now on. So it's exactly same recurrent neural network. The only difference here is we have a memory cell. And a memory cell has to have the capacity of writing or reading or writing operation, right? So for that, it will have some gates, and we'll introduce how those gate works. So we have, it is the same neural network. We have A, multiple copies of A, but now there is, in the image, as we can see, there is a lot of complex operation or complex stuff going on here. And it is not really complex if you just think of the main intuition. So you will explain how it works. So LSTMs are explicitly designed to avoid the long-term dependency problem. So how do you avoid it? We introduce a memory. And by that memory, we store the information that we want to store, and we remove the information that we want to keep. So we know that we have a connection from our previous step, but the amount of information that we are going to consider from previous step, that we can now control. It's just not going to directly impact my state directly. It has to pass through a gate and control, and then as it passed through a gate, now we have a control over that information. So if it is exponentially large, I can just avoid it. And I'll just can say, okay, I'm not going to take you because you are going to ruin my learning. Something like that. It's a very simple idea. We have a memory, and that memory now decides what to take and what to forget, that kind of stuff. And we will explain how that in the design process works. Now, a memory. What is the memory? I mean, it's a very simple idea, but if you think of your computer memory or something like that, what is the memory and what property a memory should have? What is the common property every memory should have? And what it takes to be called something a memory? Any thoughts about that? It's yes, I think I got some answer. Yep, a memory should be able to store information. And okay, that is one way. That's the first thing, that we have something to store information. Then what can we do with that information? We can read information to that memory or write something, right? A memory also allows this read and write operation. It gives us a storage, and we can read, we can make a read operation or write operation in that storage, right? That's it. And that's what we need to build a long short-term memory network. Okay, so long short-term memory network has this memory cell, and we have this idea of memory cell, and it is the everything that is going on here. So here is a line going on in the top of the image, and I don't, okay, let's forget about it. So that line represents the memory of LSTM. And so what going on here is we can, so there at each time step, we have a memory cell, and that memory cell can do this read or write operation. So how it's going to work, like, so what happens? We take some input from our previous step. We have, I mean, memory has, every network has at each time step has its own input, and it also gets some additional input from its previous state. Now, how much information we want to take from previous step is controlled by a gate that is called forget gate. So you want to so in the step t minus 1, so we have two steps, t and t minus 1. Just imagine that we have two steps, t and t minus 1. T is our current step, t minus 1 is our previous step. Now t minus 1 also has a memory, as we discussed that each step has its own memory, one cell. Okay, now we want to take something from there, from the old memory, because that's how it works. It sends some input. Now, but that input will be controlled by a forget gate, that we want to forget something from the old memory. That's why we have this gate that controls the information flow. And then we also want to take new information, but we are not going to take the information, all of it. We will also have another gate that is called input gate that controls how much new information we want to take. So there is one information source that is old, which is previous step, and there is another information source which is new information, the current time step. So we take information from both steps by by passing it through a gate, and that gate tells us how much information we want to take. Okay, so we have three gates: input, forget, and output. Because eventually, what happens? We need to output something. So, and forget, input, and output, all of them are just a sigmoid neural network. So if you send something, send an input to a gate, it will give you a value between 0 and 1. So let's say I have an input and I send it to a gate and it gives me a value between 0 and 1, right? So if I have something like, let's say 0, that means that if we are going to multiply something with value 0, what happens? It becomes 0. So you have a forget gate, and you have a value from 0 from that gate, and then we are going to multiply the old memory by 0. That means that it becomes 0. Or we can also have output like 1. Then if you are multiplying that old memory by 1, that means that we are taking the whole old memory. Or we can be in between, something like maybe 50% of old memory or 10%. It depends on the learning procedure. We don't, as it is a neural network, we don't have to do anything by our own. We just insert a memory, insert a gate, and that gate will, in the learning procedure, the training procedure, it will learn how to control the information flow. And the intuition here is, if we have a 0 from that gate, it means that we don't care anything about the previous step. We are not going to take any input from that step. Or if we have a 1, that means that we are considering everything from previous step or older memory. Then you also have new input, but maybe your new input is not relevant. So you want to have also another gate for considering new input. So if I have a new input, I pass it through a gate. It gives us me a value between 0 and 1, and then with that value I multiply that information. And then if it is 1, that means that I take everything from that input. But if it is 0, that means that I don't really care about this input. Or it could be in between 0.5, 0.2. So this is something really, really sophisticated, as if you think of the idea how it is goes. So we are working with sequential processing, and So if you read through some sentences, maybe some in a document, not all the sentences are useful. Maybe your current time step input is not useful. Maybe your previous step is much more important. So now you have the choice to decide, should I consider my current input more, or should I consider forget get, or should I do a balance between them? All that flexibility, it gives us a lot of flexibility in learning procedure. This is one of the very foundational and seminal work in machine learning or deep neural network, where you have this idea that model now can have decide how much information it should process, how much information it should pass to its next step. Okay, now we got this idea that we have input gate, we have a forget gate, then eventually we need to sum together. So there is some old memory, there is new memory, and eventually you will output something, right? So the output will be summation of these two or addition of these two. So we take something from old, we take something from new, and we sum them up and we send it to output gate, and output decides how much information to output. So an LSTM has 3 of these gates to protect and control the cell state, and cell state is everything that we care about. Okay, so forget get, as we have discussed, it decides what information we are going to throw away from the cell state. So each copy of those time step has cell state, and we just using this forget get to consider how much information we are going to take from our previous cell state. And then input get creates a temporary memory or because we at this time step we have a new input, right? We got an input and we will create a new temporary memory, but it's not final, because eventually we have to summary together. We have this input, we have this forget, old stuff. So we will sum together and give some output. So this input will be temporary. So what we do, CT stores candidate values or temporary values that could be added to the state. Okay, so we have a memory and that goes sequentially, and we always play in between this forget and input get, and eventually we do this memory update, right? Because so the memory gets updated at each time step. So we have a forget get FT, and we multiply it with our previous state, and we have an input get CT, we multiply it our input get. So eventually we just add them together to update our memory. Okay, so this is something pretty nice. Just if you think about it, we have a memory now to each time step, and we have a cell to represent the information in that state, and you have this flexibility of updating that information at each time step. So we have a cell, and at each time step, the cell will be updated with new information and that required information. And we have 2 gates, forget and input, to control the information flow. And finally, what we are going to do, you will have an output gate, and that will also have this 0 to 1 value in between. And we just send that our new memory to that output gate and produce an output. So if we just think about RNN, what happens in RNN, it doesn't really care about any of these gates. We got some new input, we have previous input, it just takes them and computes something. It's a direct computation. And so it's something like, if you the intuition here is, in standard RNN, hidden state and new, the information that you get from previous state and your new information, you just take all of them together and compute a function out of it, right? There is no control of information flow. You have these 2 information mixed and just compute something. But in LSTM, we have this memory. That memory handles each state, and we update it at each time step. So this memory now how it why it should solve the vanishing gradient problem, because now you can just say your gradient is pretty large, so I am just avoiding it. So you can set forget get to 0 and just avoid your previous state. So it will not vanish, because it will always have something for itself from its own state. Okay, so if we read any LSTM paper in literature, you will see something like this bunch of equation. And so I can try to explain it just for a 1 or 2 minutes. So always we have two things or two inputs. One comes from previous state, which is ht minus 1. And we have new input, which is xt. And w and b, our neural network parameters. Let's forget about them for now. And then sigma, as we see here, 10h, all of those are activation, or you can think of this as activation function. Okay, so ft, it, ot, these are three gates you have for get, input, output. So for get will have a sigma, and input gate also have a sigma function, and output gate also have a sigma. So all of them have a sigma function, which gives you a value between 0 and 1. So it, if you look at it, it takes the same input, I mean, the same value, st minus 1, xt, all of them take it. It just, all of the gates have their own parameters because they want to learn separate things, separate property from the data. So then we have these gates that we understand pretty well. Now, the cell state has two states. One is temporary, another one is current memory, and another one is previous. So cell state has three circumstances, that we have a previous cell state, we have a current cell state, which is tilde, and we have a like final cell state, which is CT. So C tilde, what we are doing here, so if you look at the RNN equation, there will be 10s function there. So we have this 10s function, and it takes our new input and compute it. Look at, so this function is not a sigma. CT is not going through a sigma function. It's going to 10s function. So it's a nonlinear function that we are computing our information. So we have got this. Then CT, the fourth line, it has these two components. As I discussed earlier, that we are trying to forget something from our previous state. So what we're going to do, CT minus 1 multiplied by FT. So forget get is working on the CT minus 1. That means it is controlling how much information you want to take from CT minus 1. Okay, we got one part. Then another part is IT multiplied by CT tilde, which is your new input get will also control how much information want to take from new temporary memory. Then eventually these two sum together, and we got our final cell state, CT. And then what we try to do, we have another gate, which is output. We apply 10h function on CT and then multiply it with output gate. So this is, I mean, the equation may at the first glance seem very, I mean, I should say very, very complex, but it's not really complex. It always working on the cell state, and updating that cell state is the main intuition here. And this flexibility that you can forget the previous step, or you can decide what information you are going to process, is the key to LSTM. And these three gates allow you to do that. Okay, how do we train this LSTM? It's the same technique that you can train backpropagation through time. Now, and also we have to learn now there a little bit of complexity, because earlier we don't have these gates, we don't have to compute the parameters. Now we increase the number of parameters in the network because we have 3 new gates, and all of them has their own parameters. So you have additional parameters, and you also have input layer. And the output is exactly similar to a recurrent neural network output. You can have 1-to-1, 1-to-many, or many-to-1, many-to-many connections. All of that are possible. So just the intuition here is to always think about that RNN and LSTM are in the sequential format, or you can have them as a block. And the only difference is when you think of LSTM, you replace that block with a memory and 3 gates to control the information from your previous state and new state. So they are somewhat similar in spirit, but LSTM gives you a memory to control the information flow, and that helps a lot. Okay, and we can train it using RNN training technique. It's the same technique. And if we have a single output, that means that, so how can we get a single output? It means that the last output only matters. So it is something like this. If you have a long chain of information going on, let's look at how do you mean that you have only one output? So if you're working on a classification problem, that means the output comes from the last state, last hidden state, right? As you can see here, many to one, we have a connection from last state, and it produces an Y. So the problem that you are working on now, or I guess the discussion with Zhi Qiang, the earlier discussion, that also have the many to one connection. That I mean, in the RNN perspective, that we have input sequence, it may have 10 tokens or 20 tokens, but we have only one output, and we take that output on the last state. And if you have a problem that involves output at each step, that means that you have to work with that kind of problem. So that is called sequence leveling. Okay, so now any question on these two networks, LSTM or recurrent networks? Okay, so move on to this, using these networks to solve some NLP tasks. So our lab works on some of the interesting social NLP problems, and we can give you some example about that. We work on something called hate space classification, or which is also close to sentiment analysis. So given an input sentence, the model has to decide, is it positive or negative, or is it hateful or non-hateful? So those kind of problems. Then there is also another set of problems, that is document classification. You have got a document and maybe a news, and you want you want to build a classifier, and that is like that predicts, is it the news about a technology or a sport or entertainment? So that kind of. Then also we work on like AI safety, like if you have an NLP system, how safe the system is. So like gender bias and all those kind of systems. Then Mission works a lot on this explainability, or like hateful meme detection, which also involves like image processing and language processing, like text processing, both of them. So given an meme, you have to decide, is it hateful or not? So there is a lot of interesting problems involving classification, prediction, generation, and it can also become multimodal, which is text and plus computer vision. And we can solve those kind of problems using recurrent neural networks. So when you see a sequential information or anything that involves sequence, we can process that information, or we can learn those something from that information using a recurrent neural network. So the text classification pipeline, I guess already you are aware of that we have an input, and we process that input and send it to a text classification model, and then we get an output. That's the block 3 stages. So we have input, we have to process that input and then send it to a model, and the model will give us an output, right? So now what can we use as features for RNN? Because I have not discussed about what we can use as a features for recurrent neural network. We mostly talk about how the architecture looks like and how we can train them effectively, or how can we solve vanishing gradient problem. But in practice, when we try to use them, what kind of features we can use, or any intuition that we have seen in our early session about convolution neural networks or embeddings. Can we use those features here? Any idea what kind of features we can use here? It's a question for audience. You can also unmute yourself and just share your thoughts about this problem. That what kind of features you can think of using with RNNs. Now that we know what kind of features we can use with convolutional neural network.
Is it not like very similar? Is it not the same as CNNs?
Mm-hmm. You mean the
Like you
network or
can,
features?
no, the features. Like, are you not just using the words?
Yes, I'm using the words. And you are right that they should be similar because CNN also works with words and RNN also works with words. So they should be similar. But what kind of features you are planning to use? Do you think that embeddings will work for RNNs? So the answer is yes, we can use any feature that we use for convolutional network, we can also use that for RNN. And so if you just look at the feature idea of feature space or feature generating features, so we first have some input sentence and it has some tokens. And for each token, we get some embeddings, right? We vectorize it. I mean, we can't process the string or text. So we convert it into a numeric value and we get some embeddings for that value, a vector for that. Now, CNN works on like a convolution operation on that vector set of vectors. And in RNN, what we do is we just connect them in a like sequential manner. RNN will take each vectors and process it sequentially. So whatever you have in the feature space, it doesn't matter. So RNN will work in its design process and convolution will work in its convolution operation. So we can use globe embeddings, word-to-back embeddings, or any embeddings that we have learned today for this feature space. And sometimes you also want to, feature is not something that is very like always the same. If you have a different problems, you may want to have different kinds of features. Let's say for head space classification, maybe understanding emotions are useful. So we can also have like emotion feature in the network. So that kind of, so always, when we work on our research problems, we always, in deep learning solutions, we try to think of as in our first session, we discussed that the feature space or the input space is very important. And the true power of deep learning lies in its descriptive power, that how well you can represent your data. So if you can start from a very good feature space, that helps a lot in the learning process. So a lot of time we think of how can we improve our feature space. So if you have a head space classification, that means that in the sentence, you may have some tokens that are hateful. So if you can emphasize on that, that may help the learning. So it is not something that we always use the embeddings. We have the embeddings always there, but we also want to go for additional stuff that can improve our learning. And all of that, you can't really develop a new neural network every day. So the research goes into this perspective that how can we improve the input to the network? How can we improve the processing of the network and the problem scenario, the problem that you are currently working on? Okay, we'll discuss more on that part in the Jupyter, not in the Colab notebook. So for features for sequential modeling, you can use embeddings because embeddings are just for each token, you get some vector and then RNN will work on them sequentially. Now, it is very, very important to note that globe or word-to-back embeddings, they do not have sequential order encoded in them. This is very important to note. So our input layer has no sequential order going on there. because input layer is just an embedding layer. So it's just bunch of vectors and they have no connection in between. So if you just take a globe, it's just a huge matrix, right? And at each index, it has one word. I mean, it represents one word. So so when we just query about those index, let's say I am looking for now a word go to sleep. We go for that go and we take, let's say, some vector from there. Sleep, we get some vector. And there is no connection at this moment with these two vectors. It is just a static vector. But when we send it to RNN, an interesting thing happens that as RNN is a sequential processor, you can think of that as RNN is a sequential network. It works it maintains that word order and it builds that connection. So even if we don't have the sequential property in our input space, in those hidden layers or hidden, RNN layers, we build the sequential dependency. And that's what makes them a powerful network to understand language, to understand the context or semantics. And you can't solve this problem with our standard neural network because they don't have the sequential property. And we know language has sequence matters. Even if you look at convolutional neural network, they don't have sequence, but they also have this, a neighboring property that you always run this convolution operation with your neighbors. So that means that maybe you have 2 words in consideration or 3 words in consideration. So this kind of like neighboring or word order and this kind of information is really helpful to learning. And it's the holy grail of sequential modeling is this context, the consideration of that you have a network that can understand the sequence, that can understand the dependency between among the words. And then we are not going to discuss this today, but if you just Google for some time that today's NLP, how can we build a sentence classification tool, then you will for sure have this term pop up on the window, pre-trained model. So the idea of this pre-trained model is it just, let's say we have a very big network or large network, and that network we processed on with a huge amount of data. So what we are going to do, we will take that network and use it for solving another task. That's what pre-trained model is. So Globe is, you can consider Globe as a pre-trained model. So note that we are using Globe here as feature extractor, but Globe was earlier trained on billions of web data, right? Wikipedia data. So that is a pre-trained model that you are using pre-trained layer, one of the layer, not all of them, but output layer of that group. So the pre-trained model is very, very powerful, and we are not going to in details about that, but you can Google about this stuff and learn more on this. So pre-trained model has this pipeline that it has this language model. Globe is not a language model. Globe is not really a language model, but if you think of BART in NLP, that is a language model. And then we take that language model and use it and fine tune that model for solving our classification task. In fact, in our lab, most of the works, that we are working on now, all of the team is using one or two language model. Every single team is working on language models. We need this language model to develop a good quality NLP system. So this is something that you can consider. And it is fun that you can develop this language. You can train your own model or develop a classifier within 10 or 20 lines of code. And there is a library called Transformers. It is famously known for large language models. And if we just take some bunch of codes from there, some lines up and here and there, you can train a model from there. So you already enjoyed the coding session with Zhi Qiang about this convolutional network. It has a long course, right? Even if it has some long course, it's still very small. Like you need to maybe 100 lines of course. But with pre-trained model, the task is much more simpler. So why I'm sharing this is to motivate the idea that today's NLP is very advanced. Like it's also pretty easy and it also pretty hard. It goes I mean, if you want to develop a system that if you just want to develop something and you want to develop a cool app that has NLP in it, and you can do it within writing like 50 lines of code. But if you want to do research, that's a different kind of discussion. But if you have a course, maybe you want to do something with NLP or deep learning, then you just need 50 lines of code to develop something cool. Okay. We can take questions or maybe take a break, and after that we'll discuss briefly on how to train a recurrent neural network, and I'll share some codes. And I guess the discussion will be pretty short because you already had proper idea how a data, how to develop a network, or so all of them has the same property. So it's not really hard. If you can train CNN, you can also train an RNN. Should we take a break or we should continue? Okay, I will share new screen. Okay, do you have any questions on this RNN and STM? Okay, before starting the next session, I have one question. I mean, I should just get that straight for everyone that attended the session. So what is the main difference between an RNN and a neural network? Typical neural network or a standard neural network? Anyone can answer. What is the main difference between RNNs and standard neural network?
There's the time dependency factor for
Yes.
RNNs.
Exactly, that you have a connection from previous state, the feedback loop. And what is the main problem? What is the limiting issues with RNNs? What makes RNN train hard in practice? I mean, what problem we face when we try to train an RNN?
There's the possibility of it like getting very large or very small because of the factors and whatnot.
Yeah, so the gradient can explode or vanish. Yep, that's cool. And there's also another issue
that you cannot parallelize.
Yeah, that's a very important problem. And yeah, it's a today's machine learning with all these fancy GPU and all that stuff and matrix computation. Parallelization is very key to today's deep learning, that we have seen that large models and all that fancy things they're doing. And with RNNs or LSTM, even with LSTM, we can't parallelize them. So we have one problem that RNN suffers from vanishing and exploding gradient. And the problem is it is slow as we cannot process it. And then finally, what makes LSTM great?
The ability to like, select specific information that you need.
And from where? Information from where?
Not very sure. From the input, I guess.
Okay, so RNN has two inputs. I mean, RNN has two inputs in the sense of processing. I mean, all the network has only main input that you provide from your input source, a sentence. But in the sense of processing, RNN has two inputs. One comes from previous state, one comes from your current state, right? So previous state is a hidden state, that's what we have. And so the information source should be these two, the previous hidden state and your new input source, right? With these two sources, you have the flexibility of deciding which information I'm going to use. you are going to eventually use both of them, but you just control it or manage or take as much as you want. So it's a memory, and it gives a lot of flexibility of storing information. And it also solves the vanishing gradient problem. Okay, cool. Now that we know the basics, that RNN works on sequence, standard letter can process the sequence, and RNN, we cannot train RNN because they have the issue of vanishing exposing gradients. And to solve that problem, we introduce a memory cell inside RNN, and that is called long short-term memory network. That's the summary line. But there is one final touch to this, that if you read machine learning literature or the books that you are going to read in maybe some future, they talk about this idea that parameter sharing. So this is very important to note that RNN, for all the time steps, I have said it multiple times, that we are copying the same network. So it means that all the time steps share the same parameters. This is a very key ingredient for training them in practice. And you should also keep this in mind, that RNN has parameter sharing. That means each step is just simply copying the same network. It has, all of them share the same weights. And we can go into all the details, why we want to do that and all that stuff, but you can study it more later maybe. But parameter sharing is a key property of RNN to make them work in practice. And yeah, that's it. Now let's look at how we can build them with today's deep learning library. Okay, here we go. Can you see the Jupyter Notebook?
Yes.
Okay, I want you guys to help me with some interactions, because it's very easy. The amount of work you have seen in the early session, so it's just the same stuff. You will follow the exactly same kind of idea. It just maybe one line of code will change if you just think of it in terms of coding. But there is a lot of thinking goes into it. So we are working with recurrent neural network for sequence modeling, and human language has sequence. So we are using RNN for capturing those sequences or processing sequences. And it has many applications, including language models, image captioning, visual question answering, poetry generation, code generation, or maybe just a dialogue systems. And so RNN architecture has these feedback loops in it, and we have different kinds of RNN. LSTM is also a recurrent neural network. So what are the features that we can use for RNNs? That we have studied these embeddings, and we can use those embeddings as a feature for RNN. And that is kind of a now people, if you are doing research on today's NLP, maybe you are not using those embeddings anymore. You are using pre-trained language models, but it is good to know about those embeddings because they are also some kind of pre-trained models. So those embeddings will give us some features, and we will send it to RNN to learn the underlying regularities of data or context from the data. And so to learn, we have to train the network, right? So the technique is called back propagation through time, because it is back propagation. The time thing idea comes from this, that you have a time dependency, right? So you back propagate, but you also rely on the time specific computation, that all the previous time steps you consider, and that's why it is called back propagation through time. But in terms of computing derivatives and all, the idea of back propagation is exactly same. And we have seen that RNN has activation function, which is sigmoid for gates, 3 gates, and 10H for the input memory cell. So for the RNN state. And we don't use ReLU here. So I should say that we don't use ReLU because it's not really, we don't use ReLU. ReLU is used for convolutional neural network. We do not use ReLU typically in RNN. And then one of the limitations of RNN is discussed so many times, that is gradient vanishes when dependency arises. And to handle that dependency, I'm just giving you a summary again. We can solve vanishing gradient problem. We have this vanishing gradient problem that when you have a long dependency, that your gradients become 0, or it could be exploding. That means that your gradients become infinitely large. To solve that problem, we have this technique called gradient clipping or norm clipping. It just, you make your gradient always in a certain threshold, so that if you multiply them all together, they are not going to explode. Okay, and that's not really a very sophisticated solution, a workaround to train and in practice. But long short-term memory network is much more sophisticated, a very cool network that was introduced by Schmudhofer. He's a very influential scientist. Anyway, so long short-term memory network has this idea that each state has a memory cell, and that memory cell stores how much information we are going to take from previous state, and how much information we also have at our current moment. And then that's it. And we, as a feature, we will use globe in our today's discussion, I guess. And pretend language model, we are not discussing them today, but it is something that you can study if you are interested in these problem setups. So now we will do some coding, that we are working on a classification task. And I'm not using the same data set as provided by Minshan, because I have this data set. I mean, I wanted to have a code that is very small in size, so that you guys feel encouraged. Oh yeah, I can train you can networks, and it's pretty easy, like 10 or 20 lines of code. So I mean, there is, if you have looked at any kind of, let's say, deep learning course, there is, I mean, all the Python stuff always starts with some library. So we have NumPy, and it's a good library. And I'm using TensorFlow. Today, you can also use PyTorch. So you can use any of this library if you as you feel comfortable. And we are also using matplotlib to plot the data. Okay, so it's pretty easy because we are working on IMDb reviews, and so it just positive and negative review. So we have so you can TensorFlow has this library function that can help you to load the data. So we write this line tfds.load IMDb reviews, and you give some bunch of arguments, and you can get the data. So this block is working with getting the data. So you can, so note that we are now working with the data set that is stored in TensorFlow. Okay, so we are just loading it from there. Maybe you want to use your custom data, as we have seen in convolutional network discussion. Then you can use a similar script that Zhi shared with you guys. But okay, so we have got data. That's cool. You can get it from some TensorFlow store, or you can use your own. So always machine learning is concerned with two things. One is trained data set, another one is test data set. So trained data set is for model training. Test data set will be used for evaluating the performance of the model. Okay, so and this data set has some, as you can see here, it has some text and some label that we are given an input text and we want to generate, and it also has a label. So you will use this data for model training. Cool. Now, always when we develop a machine learning model, we should inspect our data, that how it looks like. And because as you will develop the network, you need to decide on how many, what should be your vocabulary size, what is the maximum length of your input sentence, and there are all kinds of stuff. Is it some like it could be some HTML code, so maybe HTML code you need to process the HTML code, or it could have some punctuation marks or some we work a lot of, let's say, Twitter data set. So they have a lot of noisy emoji and all that stuff. So maybe emoji are not useful to understand the context from the sentence. So you want to remove them. So it is always good to inspect your data and look at them and process them before sending it to the network. It is very, very important. There is a whole, domain available for this study, which is data science. They work with data processing and all that stuff. So in machine learning, we don't really worry about this much processing, but you should spend some time looking at your data and how they look like. In our data, we have a text and we have some label. That's it. It's a classification problem, and it has 0, 1 level. Now, we have a, let's say in our data set, we have 5,000 samples, right? So when we train a neural network, we don't really throw all the samples together to forward or backward propagation. There is an idea called mini batch gradient descent. The idea involves that we split our data into multiple batches. And let's say we have 64 or 128 samples in each batch. And then we just train it in each, iterating over all the batches, okay? So that's why you are here. You are using batch size 128. And then we are shuffling our data set so that we have some randomness in the data set. So we have trained data set, we have test data set, we are using batch size. So it will return us a list with containing each index will have 128 samples, right? So this is very simple idea. You have a, let's say 5,000 samples, and it's a 5,000 samples in a list of 5,000 sentences. What you are going to do here, you are going to create you are going to separate them into multiple batches, and the batch size will be 128. Okay, so that's we have now got the batch size. Then we have to do a little bit more work before training the network, because after getting the batch size, the next job is to, still your data is in a raw format. It's just input sentence, right? That network can't work with indirect string that you see in as input sentence. We need to convert those strings or those tokens in some numeric value, right? For that, we use this tool called from TensorFlow, text factorization. So the idea is pretty simple. Think of it as a function. That function takes an input and it returns. So that input is a sentence and it has some tokens. Against that, or each token, it returns a numeric value. Okay. Now, maybe I guess by now you are familiar with the idea that you need to build a vocabulary, because the idea of developing how do you index those tokens in your corpus or in your training data, right? So if we want to assign a numeric value against each word or each token, we need to first develop an indexed or vocabulary, right? A dictionary that, okay, number 1 has go, number 2 has sleep, number 3 index we store is, number 4 something else. So we index all of them in some dictionary. Okay, we got it. So now there is another idea, which is to just simplify the problem, that we sometimes define our vocabulary size. The idea is that you may have billions of tokens, but you can't use billions of token model training because you don't have that memory and all that stuff. So you're just using only 1,000 tokens. So here what happens, if you look at here carefully, in our vocabulary we have some words, against them we have unknown token. So we have some words, against them we have unknown token. That means that we are not considering that word. You will find this in all the text processing in NLP, that you have some words that they do not have any index in your vocabulary. So those words will be will have this unknown token. And the rest that have an index in the vocabulary or dictionary, that will have they have their value. So eventually it will look something like this. that maybe there was some token and we replaced with some numeric value. And there is something very interesting here. What happens? The step is something like that. We have a vectorizer which gives us some numeric value, right? But you also see here, there is some zeros at the end added, additional zeros. So why we have some zeros here? Any intuition for that? Any idea why you have some zeros here? So each of this row here is representing a sentence, but why we are inserting those zeros?
Padding,
And what do you mean by padding?
like they're not all the same length. So to make them the same length, you have to add the zeros.
Yes, exactly. So they are not all of them are the same length. So we want to make them fixed length. And for that, we are adding some zeros. Exactly right idea. So we have those input sentence, and eventually we just converted to them some numeric value and also made them fixed length by adding some zeros. Now, as I said, that we have a vocabulary. Not all the words in the vocabulary we are going to use them for model training. So if some words we are ignoring them, then it will have a token called unknown token. That means that you search for the word in the vocabulary, it is not available. We search for the word, it is not available. Okay, it just that we don't have enough memory to store a long vocabulary. That's the consideration here. So we just use a small vocabulary to finish our task. Now we have already vectorized our input sentence to some numeric value. That means that it is more or less ready for sending it to a network, because network can work with numeric values. Okay, so how can we create a model? The idea, okay, now this, when I was starting machine learning in the early days, I always get confused with the idea, what is a model? What is a network? What is an architecture? What is an algorithm? So just this is very confusing in sometimes. So model is, in machine learning, model is something that can feed you data. So machine learning is all, there are other ways of defining machine learning, but you can define machine learning as that, it could be something that feeds you data. Okay, that can explain you data, that feeds you data. Okay, so it's just a function that feeds you data. Now that is a model, and a model need not to be a neural network. A model could be a very like you have other decision tree is also a model. It could be okay, but RNN is a network. It's a recurrent neural network, and when we talk about architecture, what is architecture? So as you have seen that RNN has like multiple time steps. Now, how many time steps you are going to consider? It's a design choice, right? Then how many layers you want to have in RNN? Because we already discussed that in neural networks, we can have multiple hidden layers. Like how many layers you want to have in RNN is also another design choice. So those are the architectural choice. So if I have a 2-layer neural network, that means my architecture has 2 layers. If I have a 5-layer network, that means my architecture has 5 layers. If I have 500 neurons, that means it's my architecture choice. But all of them are recurrent neural network. All of them are RNNs, but different architectures. And eventually the algorithm, what is algorithm in the machine learning area? The algorithm are mostly involved with the idea of training. When we try to train a network, we use some algorithm to do optimization or to learn regularities from the data. So that is mainly we are in today's machine learning, we mostly use stochastic gradient descent algorithm for training the network. So we have got the idea about model, network, architecture, and we have an algorithm for model training, which is SGD. Okay, now we have input in the model, and then we have text vectorization that I have already showed to you. It's just converting those input tokens to some numeric value. And then we have embedding layer. The embedding layer is just like if you have a list array in Python, if you have or in C++, if you have a array, or maybe a dictionary, in Python. What it means that you query for your index, maybe 5 is your key, and you query for that index, and embedding returns you a fixed dimensional vector. Embedding always returns a fixed dimensional vector, and in general it is 300 dimensional vector. So for each vectorized token, 5, 8, 3, 120, 35, we query in the embedding layer, and embedding layer gives us a 300 dimensional vector. So if you have 5 of them, then it will be 5 into 5 into 300, something like that. Okay, it will be something like 5 tokens, each of them has 300, so the vector will be 5, 300. This is something like that. This is what we call by dimension. So it will be 5 into 300 dimensional vector. Then eventually you have got your input, and it will send to a recurrent neural network. As you can see here, each neuron has a connection to its next neuron, or then it goes the connection. And it could be bidirectional. So the idea of bidirectional is you can start from left to right, or you can start from right to left. I mean, you can start from the last position of your sentence, last token of your sentence, or you can start from first token of your sentence, or you can apply both. So usually we apply left to right because that's how sentences are always processed. But in some study, it is found that if you apply both, that left to right to left, it also helps to get idea from left side and right side. That means that you have proper idea. If you know that what is going to be your next word or previous word, then the middle word is much more decisive, right? Just think of this sentence: I blank to school. So I blank to school. So this is, I mean, now if I give you a sentence and you are given the task of filling this sentence, your general choice will be go. You can't really use too many other tokens. You have a very constrained choice. So it means that if you have information from both sides, that improves your understanding of the language. Okay, you can process the language better. Then eventually, after sending it to a recurrent neural network will has some its hidden layers, and we finally send it to a dense layer and do the classification, which is softmax. Okay, so that's how it works. We have our input, we send it to text vectorization, what we have already done. Then we'll send it to an embedding layer and put it inside a neural network, recurrent neural network. And finally, those outputs from the recurrent neural network will send it to a dense layer, and dense layer will give us the classification. Okay, so how many lines of code it requires to write this stuff? I guess maybe 6 lines of code. You can create a model writing only 6 lines of code. That's so easy, right? And you can also look at how your model looks like. That here I print model.summary. That will give me a summary. So our first layer is text vectorization layer. Then as we discussed, we have an embedding layer. Then we have a bidirectional RNN. We are using an LSTM in practice. It is LSTM. And then we have some dense layer to make the prediction. So that's what we have discussed here, and it is exactly our network. Okay, let's look at it one by one. So we have an encoder that will do the text vectorization. Then we have an embedding layer that is just a lookup table. It's just a lookup table for each of those vector or text vectorization. For each of these index, we want to look up in the embedding layer and gets a 300 dimensional vector. So this is just simply your embedding layer. Okay, then you also define that what will be your output dimension. Here I can set it to 300 dimension, right? And then here it is also, there is another thing it is taking, it is called mask 0. So the idea here is, okay, so you have these, let's say we have another sentence that only has 2 words. I sleep, that's it. Now then these words will be 0. They will be padded by 0. So the mask 0 is the idea that you want to remember that which position has 0. That's it, nothing difficult. So we have encoder, which is just text vectorization. We have embedding layer, which is our second layer, embedding layer. And then we will send it to a bidirectional LSTM. So it is how you can write it tf.keras.layers.bidirectional, and you define LSTM with 64 neurons. Now it is important that if I have defined that my last layer, previous layer output will be 300, then this must be 300. Otherwise it will not work. So let's try this. See, oh, I haven't really installed those stuff. Okay, let me do that. Okay, encoder is not defined. Okay, so you will define encoder. Just define encoder. Okay, we have defined encoder. Now we can run this. Okay, okay, we can do all of this stuff. I guess you have to do them. I'm trying to save some time. Okay, we got this import. Now we are taking our training data, which is train data set and test data set. And then data set is being downloaded. Let's wait a couple of minutes for that, maybe. Okay, I can keep explaining the stuff here. So we have embedding layer. Then the argument here is if you have a 300 output dimension, then your input dimension should be 300. So that dimension should match. And then we have another dense layer. And finally, you want to make only one output, which is 0 or 1. So that's why you have a dense layer with only one neuron. And then we also have this dense layer, which have 64 neurons. We just, after processing with LSTM, we send those processed hidden states, last stated output to a dense layer is just a simple standard neural network. So we send it to a neural network, and then finally we send it to a softmax layer, which has only one neuron to get us the classification output. Okay, we have load the data set now. We can do this. Done. Okay, it works, right? So let's say we have 64 here. Wow, it shouldn't work. Oh, if I try to train it, then it shouldn't work. Not yet. So you can define the model, but the problem will arise when you try to train it. So that's just one important. I'm not going to train it today because it takes a lot of time to train a neural network. So eventually what you can do, so we have defined our network. We have input that goes into a text vectorization, and it's just a same formula for all the networks. And then it goes into embedding, and then we send it to LSTM layer. And finally, we send that output to a dense layer and get the classification output. So as we are working with deep neural networks, that's why it has multiple layers and it becomes deeper as you go further. Okay, now there is one important thing that if you're working with fixed length sequence, I mean, if you are working with variable length sequence, it is important to do the padding, otherwise you will not be able to train the model. And so you will face a lot of dimension error and all that stuff, which is very annoying. So always try to remember that we need to convert those variable length sequences into a fixed length dimension. And for that, we can use padding as a tool. Okay, then eventually, once we have the model, that the final question will be, how can we train the model? And that involves an optimizer, a loss function, and metrics. So optimizer will, so neural network has some parameters, right? It starts with some parameter, but those parameters are not optimal. So optimizer will learn from the data. We will learn from the data, and optimizer will eventually lead to a optimal parameters, right? That's the job of optimizer. Finally, optimizer does the job of learning. But now how optimizer will act if you don't have a function to tell the optimizer that you are doing something bad or you're doing something good, something like that. So for that reason, we need a loss function, that if we make a prediction after looking at maybe 64 samples or 120 samples, if we make a prediction, then we also send that prediction to a loss function, and that loss function tells us how bad we have done the job or how good we have done the job. So, and we optimize over that losses. And then we also need a matrix to eventually evaluate that how good our training is. So matrix will tell us what is the accuracy there, and loss function will tell us what is the loss function, loss in each iteration. Okay, so you can set it by model.compile, and here we define loss function, and we define the optimizer, and we also define the matrix for our evaluation, which is accuracy. So it is, if you have got 100, let's say you have 100 samples, you got 80 of them correct, that means you are 80% accurate. So we have, for training, we need an optimizer, we need a loss function, and we will do evaluation using accuracy metrics. Okay, now once we have these two setups, we can now feed the data, and I already trained it earlier. So it takes a couple minutes to finish training. So I just trained it to show you how it works. So again, as we discussed earlier, what we are doing with neural networks is feeding our data. So that's why you're calling this model.feed. And here we send our trained data set. We set the number of epochs, that so the number of epochs means, so how many times we want to show our samples to the network. One epoch means that the one sample network sees 1 times. If it is 5, that means the network will see one sample 5 times. Okay, and then we also have test data set for validating them, and also have validation step. That means that that after doing some work with the training, then we want to see how good or bad it is. So here it is, as you can see, we have 5 epochs, and at each epoch you can look at the accuracy. So just look at this accuracy, the last, this 0.59, 0.77, and 81, 83, 83. So as we keep growing the epoch, we increase learning, that 59 to 77, there is a good jump. Then 77 to 81, that's fine. But after that, it doesn't increase much. Here we see 59 to 77, it's a good jump in the accuracy. But as you notice that after going through 2 or 3 epochs, model start learning less, and at some point it does not learn anymore. So that's when you should stop learning. Okay, so I have got around 82% accuracy on my test data set, and it's not bad. And you can play with these parameters, hyperparameters, that number of epochs 10, maybe batch size is 32, maybe you have an optimizer, and optimizer has also a learning rate. You can change this learning rate something like 10 to the minus 5. So you can do all those hyperparameter changes and see what is, how it improves your learning or impact your learning. So once we have feed the data, then we can get the results, and we can also look at the training curve. So here we plot our loss, 2 loss, validation loss and training loss against epochs. As you can see, the loss like grows. I mean, there is a huge jumps from the at the early point, starting point, but eventually at some point loss does not decrease much. It becomes kind of flat, or sometimes it becomes worse. So that's a kind of practical technique that usually 5 or 10 epochs is something community use, or most of the people will be using. If you are working with like 200 epochs, 300 epochs, that means you are doing something wrong, unless your problem is very specific. So the standard norm is using epoch something like 5, and also having this test data set to evaluate how good you are doing on unknown data set. And then we also look at accuracy, that there is, as we noticed that in the early, there is a huge learning going on. We learn so much that we, from 0, our accuracy increased to around 80, but after some point, there is not much of, we can't learn further because that's the limit. So this is how we train the network. It's not really something complex. We just need to process the data set up the network, and finally figure out the optimizer or loss function, and set up an metrics so that we can evaluate the network. And it is always good to have some plot to explain how good your learning is going on there. And I guess you also need to do a project, and we want to see some plots from there to explain your the system that you have developed, or the classifier you have developed, how good it is. So it is important. Okay, any question on that? We are nearly done. I need maybe 5 minutes. So do you have any question on optimizers or training or anything looks suspicious? So we are using LSTM network here in the network session. You can also use other LSTM network, other networks like Zhi Qiang neural networks, or there is a variant called GRU networks. You can also use them. It's really up to you. And you can try multiple networks to see which one does a good job. In your project, you want to try several kinds of networks to see which one does the good job. And it really helps to understand the problem or the limitations of the models and all that. Okay, I have a question for you guys that, okay, now why model stops learning, or the network stops learning after 5 or 6 or 10 epochs? What do you think? What happens there? Why we don't learn 100%? Or is it possible to learn 100% of the training data?
Yes, on training data, right?
Yeah, is it possible to learn 100% on training data?
I guess so.
And how that would be possible?
Okay, I have no idea.
So test data, you don't see them during training, but training data you can see. You can always see, check at your training data, and 5 times means you are looking at them 5 times, and you can look at them 100 times. And what happens when you see something in the morning every single day? What happens in your memory? Let's say you wake up in the morning and you see something every day. What happens? You just memorize it, right? You know, the bus will going to come at 9:30 always in the morning. That means that you already memorized it in your cells or all that neurons. So that will send, because you are looking at it all so many times. And as you have neural networks, it's a bad intuition, but it's just fun to think about it, that those neurons have some parameters, and those parameters are working or trying to understand the data and just compress something about the data, right? So feed them. The feed will be a good word. So our neural network is trying to feed the data. Now, if you keep training on some data set for a long time and for long epochs, that means that network is going to memorize it. And you can try this with your experiment. It would be a nice experiment that you try for 50 epochs, and after that you see what happens on your test set, because model never get to see that test set. So this is something fun when you try working with neural networks. This is something that you can always try because it's really boring. You can track this like notebook and you can develop a model. That means it's so boring and so easy, right? But if you try this kind of thing, a lot of fun idea about deep learning will emerge. Like what happens when I try to memorize my data? What happens when I only look at them only once? What happens? I mean, looking at those extremes will give you a lot of intuitions how neural network works and help you understand their property. So this is something you can try in your project to take them to the extreme and trying different learning rates extremely large, trying large batches if we have GPU and all that. Okay, so this is some idea that you can try, and you can also talk with like chat with us about how you can try different kind of networks and what you should change. And for sure, many of us will be happy to help you. Now, I mean, if I'm involved with some community work and I talk with people and there is something like, man, this is so easy, right? You are just giving us 100 lines of code. It's so easy. And it seems everything is done. And there is something, if you are undergraduate and you want to do machine learning research or AI research, and you want to build something, it looks like everything is done. You can get 100% accuracy. So how do I do something? So that is something like that. And so in those perspective, there are some idea that the contribution, you can introduce a new task that currently you are working on, that we are introducing new task for the community, and you are helping us with getting data set ready, and we will develop models on those data set and release them for public use. So that is one way to contribute in the community, that introduce a new task, work on data set. Then our team also works on like learning systems that can have flexible, fast, and very robust learning, which can do, which does not really only work on a small data set, it works on various kinds of data set. So Rui works on this kind of problem that called domain adaptation, which is you have multiple domains and you want to develop models for different domains. And then also Southeast Asian languages is one of our interest in our lab. So you work on different languages. Like most of the NLP system, if you go out there and look for, I mean, in the archive, then you will see that most of them are for English language because it is well studied always. And we are trying to bridge the gap and bring it to our Southeast Asian languages. Maybe your mother native language is also we are working on. You can help us in those kind of works, like developing NLP tools for low resource languages or for most of the world languages. So I work on those kind of problems like multilinguality. Then we also working on problems that does not really look very simple, like recurrent neural network. And one question you can ask, how can we incorporate hierarchical structure and recurrent neural networks? Like if you have a tree, how can you process a tree with recurrent neural network? How can you, like, let's say Duma propagation or hit speed propagation, anything that propagates that looks like a tree, and how can we process those kind of information using recurrent neural networks? So that is something that our team also working on. And Sean works on adversarial attacks, which is if you have a system and how can you fool the system? It is very fun that if you have a system and it makes a prediction and you're trying to fool it so that it make bad prediction, or it does not really fool by some changes in the data. And then there are works that Minshan is doing on the explainability. So it is something like neural networks, it has 80% accuracy right here. But if you take the input samples and take one input sample and send it to a neural network, like what you have trained here, it will give you an output. But if you ask it to explain the output, why it made the prediction, why it considers that this input is positive, or this sentence is negative, or this sentence is harmful, so why it thinks something like that, it's very hard to explain those kind of, so it can be a good prediction, it can be a good function approximator, or it fits data pretty well, but it's very hard with today's neural network to explain why they do something. And Soumission is working on explainability. If you are interested on those, you can talk with him. And then you can also develop tools like 10 lines of code, develop a very fun project and deploy it for real world use with some API. So our Zhi Qiang is working on generative modeling, which is like, if you have an impolite statement, how can you make it polite? How can you make it sound nice and sound good? If someone is abusive, like using abusive language, you have a chatbot, maybe a dialogue systems, someone is speaking continuously abusive language, but as a dialogue system, you can't abuse them, right? You have to be polite in the language that you are using because you are a business tool. So in that case setting, you need to develop, even if your input is something very abusive, you want to produce output that are very polite and those kind of problems, and you can build so many fun stuff. So with that, that's all. And I think I can now take questions, and if you have any.
Yeah, I think, yeah, thanks Rabu for like giving the detailed idea of how RNN works. Right. I think along the workshop, then I mean today's workshop, then I realized also like maybe there are some concepts that you guys haven't learned yet or grasped yet, right? So for example, when Zhi Qiang was teaching about data loader, then I recall that, you know, deep learning and machine learning actually differs quite a bit, right? Where like I think in like decision tree and stuff, there's no such idea as like batch learning, right? Yeah. So maybe like some concepts that if you guys are still unclear about, you guys can go and find out more, right? Such as like gradient descent, and then why we do batch learning, that kind of stuff, right? Because gradient descent will be linked to the batch learning. Yeah. Other than that, I think, yeah, me and Zhi Qiang is crafting some of the project, right? We'll probably get it done by this weekend. So we'll craft some of the hands-on project for you guys. So you guys got some experience, and then as you guys proceed with the project, you guys will encounter some difficulties or you guys will encounter something new. Then that's where, you know, we can come in and help you guys to understand better. Then yeah, as you guys gain more competence, gain more capability, right? Proficiency, right? Then perhaps when you guys are more well equipped and you guys want to tackle more of the more advanced problems, right? Then yeah, feel free to find any of us. Yeah. Yeah, I think that's all I have or we have for the day. Is there anything else you guys want to add on? Rabu and Zhi Qiang? Yeah.
No.
Okay, if not, then yeah, thanks everyone. Then we will release the videos soon. Yeah. Have a great day ahead.
Thank you so much.